for this lecture. Please circulate the attendance. You could mark your, please put your signature.
Good morning, everyone. Hope you're all rested from yesterday and ready for today. So today I'm going to actually talk a little bit about how you measure data to get PDFs, and how you process the data to get PDFs. And then we'll have a hands-on session where hopefully you can install PDFget X3 and you can actually try and do some data analysis yourself on some X-ray data. If you have some of your own data, then try and help you to process that as well. So, first of all, I'd like to give a big thank you to these two people. This is Kirsten Jensen, this is Emil Bosin. So, Kirsten did her PhD in Denmark, and then she came and did a postdoc with me. And she's now a faculty member at University of Copenhagen. She is a very excellent scientist, and Emil was actually a PhD student with me in Michigan many years ago, and he's gone on to a successful career, and he's working at Brookhaven National Lab, so I collaborate with him very closely because I work at Brookhaven Lab. And in particular, I want to thank them because a lot of the slides that I'm using in today's talk, I actually, they shared with me. So, I showed this to you yesterday. This is Bragg's notebook and the initial experiments. And on page 11, there was a Bragg peak. That was the world's first Bragg peak. But interestingly, if you look through the notebook, Bragg discovered Bragg scattering on page 11. But actually, if you look at page 5, he shows a diffraction pattern that looks like this. And this is actually looking like diffuse scattering. So actually, I like to joke that the real Bragg scattering is actually diffuse scattering because he discovered diffuse scattering on page 5. So the Braggs discovered diffuse scattering before they discovered Bragg scattering. But actually, they weren't so interested in diffuse scattering. But as I hope I conveyed yesterday, we're very interested in diffuse scattering. Okay. This is a quick overview of the 3 different ways that you can collect data from X-rays. This is the rapid acquisition PDF method, and what you need here is a very high energy. So the wavelength of the electrons are something like 0.1 angstrom, so they're very short wavelength X-rays, and we get them from a synchrotron. We place a sample here, we place a 2D detector here. This is just 200 millimeters between the detector and the sample. So this gives us very low resolution in Q, so low resolution in reciprocal space. We get broad Bragg peaks, but it allows us to very rapidly collect data with very high Q max. So we can collect data over a wide range, but with a low Q resolution. And this is actually our preferred way of collecting data most of the time. Of course, in order to do this, you have to have a synchrotron. And if you don't have a high-energy synchrotron, it's a little bit difficult. Now, there's no high-energy synchrotron in India, but you can actually make use of synchrotrons around the world by applying for beam time. And actually, many beam lines have a mail-in program where you can actually send your sample by mail, and they'll measure the data and then send the sample back and they'll send the data. So just because you don't have a synchrotron here in India, don't believe that you can't do it this way. And we also have a very good access to the Brookhaven synchrotron, and so actually we can help you. If you send samples to us, we can often measure and send the data back to you. In order to access that mode, you should just email me. Now, this is also using a synchrotron and a high energy source, but this modality is one where we have a point detector that we move as a function of angle. So this is Stefan Kitscher, who used to work at CHESS. He's in Canada now as a professor. And we, together with Stefan, myself and Stefan, we did the first very high Q measurement, X-ray measurements. And we did it with this setup at CHESS, which is the synchrotron in Cornell, which is in New York, in the US. And here we have what he's doing. We wanted to do that because we wanted to suppress the thermal motion of the atoms. So we cooled the sample to very low temperature. And then this is this thing has a beryllium window on it. Beryllium is a very low atomic number metal, and it's very penetrating to X-rays. And so the sample is sitting inside here. And what Stefan is doing is he's working on the detector, which was a germanium point detector. And so what happens is that you collect a data set in here by actually rotating this. And you can see this big wheel here. This wheel rotates and the detector goes in a circle around here. And so we collect the data one point at a time. So this method of collecting data is extremely slow. It takes many hours to collect a data set, even at the synchrotron. But it does give you very high Q resolution. So if you need high Q max and high Q resolution, you can do it this way. And there are other diffractometers around the world where you can do this. For example, there's a high resolution powder diffractometer at ESRF in France. And again, these facilities, you can apply for beam time by writing a proposal. And if it's successful, you'll get beam time. Of course, you still then have to travel to collect data. Finally, you could actually get very high quality PDFs from laboratory data. So this is actually an X-ray diffractometer, which was a homemade one in Germany. And there's the X-ray source, and there's I think a monochromator in there, I'm not sure. And then the sample sits here, and then here's a point detector. And this one, the detector's just rotating in the horizontal. So the key thing to actually do PDFs in laboratory instruments is that you have to have a molybdenum K-alpha or a silver K-alpha source. So the actual X-ray tube needs to be moly or silver. But the quality of the PDFs from these instruments is just as high as you get from these, but you have to measure for a very long time, so really many hours. This is actually showing the PDF from a quasi-crystal material. So it's like this, it's a powder of this quasi-crystalline material. It's a metal, holmium, magnesium, zinc, and you can see it has a pentagonal face here, so a five-fold face. So this has five-fold symmetry, and it's actually a quasi-crystal. But if you put it on this X-ray machine and you measure the data, you get actually a PDF that's extremely high quality, just as good as you get from a synchrotron. Okay, what about the synchrotron? So let's see, I think I'm going to discuss about this actually a little later. So let's go back to some very beginning, like what are the different ways that X-rays are generated? So this is background, and some of you may have this background, but maybe not everyone does. So in 1895, this is when Röntgen discovered X-rays, and basically what he was doing was he was interested in accelerating electrons. So he had a cathode here, and it was under a high voltage, and it would emit electrons. The electrons would fly through this evacuated tube, and it would hit into tungsten. And when they hit into tungsten, what happened is that these X-rays came out, and he had a film sitting on the desk of his lab, and the film was actually in an envelope, so it was not exposed to any light. And the X-rays actually exposed it. That's how he discovered them. So it was serendipitous. He discovered them by mistake. But very quickly he started investigating their properties, and there's a very famous picture of his wife's hand with a ring on it. These days, X-ray tubes look like this, and they're basically the same design as Röntgen's. So you have a filament, which is a piece of metal, a very thin wire of metal that's coiled up, and it's heated to very high temperature. And when it's heated to very high temperature, the electrons kind of bubble off the surface. And then there's a very high voltage accelerating voltage, which then accelerates them away from the filament, and it hits them into this target, which is a metal. So in this case, it's a copper metal. And the copper, this is dumping a large amount of energy into the copper. So typically these tubes are 1 or 2 or 3 kilowatts. So they're generating kilowatts of power. And nearly all of that power turns into heat. Only a small amount of it actually turns into X-rays. So you have to remove a huge amount of heat. So actually water flows in here, flows up here, and this anode is rather thin, and then it flows out through here. So there's continually water cooling the anode, and if that water fails, the anode will very rapidly melt. The X-rays then come off here, and what we do is we take them at a very fine angle, glancing angle from here. So you can see that the electrons would hit here, the X-rays would come out here. They go through again, beryllium window, which is this low atomic number metal. And they come out. So this is what it looks like in practice. This guy here is actually the beryllium window. And this thing usually bolts onto a housing, which is it's a lead-lined housing because it's supposed to shield. So only the X-rays are obviously very harmful to you if they hit you. So you put this whole thing inside a shield, but you can see that it's basically an evacuated glass container with a filament, accelerating voltage, and then a metal target. It's exactly the same as what Röntgen did in 1895, and they work actually very well. The big technological development recently is micro focusing. So what the manufacturers have been able to do is to focus the X-ray beam onto the target in a very, very thin line, and that gives you the most intensity, the most photons into a small space as possible. It also puts very high demands on the cooling. So how do the X-rays actually appear? How are they generated? So what we have is a very high energy electron beam. So this is the electrons that have been accelerated to high voltage. And then the metal is made of atoms, obviously. So these are atoms, and the X-ray comes in. This is supposed to indicate there's a nucleus, and then these rings are just signifying electrons that surround the nucleus. So this accelerated electron comes in, and there's actually 2 ways that it interacts with the atom. So one way that it interacts with the atom, well, it's always interacting with the electrons primarily, but one way that it interacts with them is actually there's a decelerating voltage. So there's some kind of scattering and a deceleration of the electron, and any charge that accelerates or decelerates actually emits radiation. It emits electromagnetic radiation. And so if this thing gets scattered in some direction, or if it actually gets slowed down, both of those are changes in its velocity, and there'll be electromagnetic radiation emitted. And because the high energy of these X-rays, the electromagnetic radiation that's emitted is actually in the X-ray region. So this is called breaking radiation, or Bremsstrahlung, which is the German word. And it gives a continuous spectrum, as you'll see in a minute. There's another way that the X-rays can interact with the atoms. So in the atom, the electrons in the atom are actually in eigenstates, quantum states, so they're in stable states. And what can actually happen is that the primary electron can be absorbed by the energy from the primary electron can be absorbed by this electron in some energy level of the atom, and then these guys can be emitted, and then that leaves a hole in the core level of the electron of the atom, And what will happen then is one of the outer electrons from the atom will fall down into the core level. So these levels are at higher energy and they're further out, physically further out in the atom. So we've created a core, it's called a core hole because it's a hole in the core electron band. And an electron from a higher level falls back into this. And what's emitted then is you have to maintain energy conservation. So this electron is losing energy, and what it does is it emits an X-ray photon with exactly that amount of energy. That's called characteristic radiation, and it has a very sharp line in the spectrum because it's coming from a very specific transition between the energy levels of the atom. So this is what the spectrum will look like from something like an X-ray tube. So you have this broad spectrum here, which is the Bremsstrahlung, and it's kind of this broad, slowly varying spectrum here. And then you have these sharp lines, and these sharp lines are coming from these transitions between the energy levels of the electron. And you can see that what happens if you increase the accelerating voltage of the electrons, let's say you start at 25 kilovolts, so you're accelerating the electrons to 25,000 volts before they hit the anode, and you get this spectrum here. And if you accelerate further to 50 kilovolts, so you double the accelerating voltage, what happens to the Bremsstrahlung is you get much more Bremsstrahlung, and the peak in the Bremsstrahlung kind of shifts in its wavelength. So this is wavelength here. But these characteristic lines, they never move, they never change their wavelength regardless of the accelerating voltage. And that's because the wavelength or the energy of these guys is completely determined by the energy levels in the atom that are excited. I'll come back to why there are two of them in a minute. And then what happens if you turn down the accelerating voltage too much? Here we've turned the accelerating voltage down to actually below the absorption edge of that atom. And if the accelerating voltage is smaller than the energy it takes to excite one of those core electrons, you simply can't excite a core electron. If you can't excite a core electron, you can't create a core hole. If you don't have a core hole, you can't get a characteristic X-ray out. So if we reduce the accelerating voltage down to 8, we get no characteristic lines. So how do we use these in practice? Actually, these characteristic lines are much stronger than the Bremsstrahlung. So most of the time we use actually the characteristic radiation. And the other nice thing about it is this line here is quasi-monochromatic. So actually what we would love to do is have monochromatic radiation, so a radiation of a single wavelength. And what comes out of the X-ray tube, it looks like this. It's polychromatic. We have some intensity at every value of wavelength over this range. But if you're at a high accelerating voltage, you can see this goes like way up to the ceiling here. The actual amount of X-rays is dominated by the X-rays of this wavelength here. And so you can even do quite nice X-ray experiments from one of these sources, even without some kind of monochromator. This is why you get more than one characteristic line. So the accelerating voltages that we're using are appropriate for exciting the K band of the X-rays, which is actually coming from the very lowest energy level. So it's the 1s state of these metals. So we've got electrons in here, the X-ray comes in, the electron comes in, it knocks this electron all the way out, it leaves a hole here, and then there are all of these different possibilities for electrons in higher levels to fall down and fill that hole. So we have K alpha 2, which is coming from the 2p to 1s transition, K alpha 1, which is also coming from the 2p to 1s transition, but these are two different of the p states. And there's a K beta, which is coming from the 3p to the 1s. And you can see there's no arrows going from 2s to 1s and 3s to 1s, and that's because there's some selection rules. You have to conserve momentum during this process, and the outgoing photon has a momentum, and so the momentum is exactly the momentum you get from going from a p to an s level. And so it's actually physically impossible to do a 2s to 1s transition that will emit an X-ray photon. So what wavelengths do we get out? So it depends what metal we put in. So these are some transition metals: copper, chromium, iron, cobalt, and these all produce X-ray wavelengths which are in similar region. They're between 1 and 2 angstroms wavelength. Copper is the most common kind of source. It's 1.54 angstrom wavelength, but you can also do cobalt, iron, chromium, for example, and these all have similar ones. You might ask, if you've got copper, why would you use one of these? And it's because actually the X-rays of these wavelengths are sometimes very strongly absorbed, and you might want to be looking at a material which contains an element which is actually being strongly absorbed, and in which case you have to switch. But nearly all the time we're using copper, until we want to actually get short wavelength X-rays, and that's what we need for PDF. So if you go down to the next row down in the periodic table, you actually have molybdenum, and that goes, now there's a big difference. It's almost half the wavelength from copper, so 0.71. And even shorter wavelength is silver, 0.56. And even shorter wavelength is tungsten. So most people who are using laboratory X-rays, they're using molybdenum, and they're using silver if they're trying to do PDFs. So one question is, what's the best source to use? Another question is, why don't we use tungsten, because this has extremely short wavelength. This wavelength is almost like the kind of wavelengths that we're using at the synchrotrons. And the answer for the tungsten is that actually it's extremely hard to accelerate the electrons to a high enough energy to actually excite this tungsten K-edge. And when you do, the number of X-rays that come out is basically proportional to delta E. Delta E is the difference in energy between the accelerating voltage and the excitation voltage. So it's proportional to that delta E to the 2.3 or something like that. So in order to get a large number of X-rays out of your source, you want your accelerating voltage to exceed the excitation voltage by as much as possible, which means the excitation voltage for the tungsten is up around 100 kilovolts. So we would need a source that could accelerate to something like 200 kilovolts. It's becoming technologically extremely difficult. So the trade-offs is, forget it. People rarely do tungsten. Even when they do tungsten, they're often looking at the Bremsstrahlung. So these are the good ones, silver and moly. And you can see that silver has a slightly shorter wavelength, so we should go with silver. End of story. Except that moly is a refractory metal. It has a very high melting point. This means that you can dump more power into the moly in your source, which means that you can get more X-rays out of the moly source. So the intensities coming from moly are much higher than coming from silver. Silver will melt if you put too much energy in, and so you don't drive it very hard. The other problem with silver is, because it's operating closer to its melting point, it actually undergoes degradation. So the electrons actually start to sputter the silver, and the silver, firstly the silver target gets thinner and thinner and fails more quickly, so your silver tubes fail more quickly. And secondly, the surface of the silver starts to become, instead of being beautifully flat, it starts to become kind of spongy-like. And then what happens then is that the X-rays can't get out, so you excite an X-ray and you want to take it off at a glancing angle, but it gets absorbed again by the silver target itself. So what happens is that although silver seems like a really good option, there are certain trade-offs with silver, and so I generally recommend that if you're going to make a setup that will be robust and will last a long time and will give you good intensity, you should go with moly. And then the trade-off, of course, is that it limits your Qmax. So your Qmax is limited to about 14 or 15 inverse angstroms, and that limits your real space resolution. But for most scientific cases, you're in good shape. You can still do a lot with the moly source. And then if you need that higher real space resolution, send me an email and get it on the synchrotron. Yeah, question?
Use iron or cobalt?
So we never do, because these actually are even longer wavelengths than the copper. So they're very not good for PDF.
But if the peaks are very close and you use long wavelengths, the separation will increase.
Yeah, so you'll get so this is the important thing. When you do diffraction, you always want to have high resolution so you can differentiate peaks. But you're working in Q space, so you're talking about high Q space resolution. But when we do PDF, we Fourier transform to real space, and we really want to do we want to have high resolution in real space. So to have high resolution in real space, you want to have a high Q max. So the Q resolution doesn't affect the real space resolution. The Q range affects the real space resolution, and vice versa. So for high resolution PDFs, you can have low Q resolution but high Q range. And for high resolution diffraction patterns, you can have low Q range, but you want to have high Q resolution. So if you're if you're doing diffraction and you're going to analyze the data with like Rietveld refinement, you're going to analyze it in reciprocal space, then you do want to use these guys, long wavelength. And if you're doing PDF, you don't mind about the resolution in Q space, but you want a wide Q range, so you use these guys. Copper doesn't have the longest wavelength of these, but it also has good refractory properties. It has a very high thermal conductivity. So it means that you're hitting the top of the anode is being hit by the electrons, and the bottom of the anode is being cooled by the water. And so a material which has a very high thermal conductivity, you can pull the heat out from it has to conduct from the top to the bottom before it can be pulled out. So that's the reason why copper is actually preferred over these other guys. And the copper, again, the copper sources you can get very high intensities from, and they last a long time, those tubes.
Tubes come in two types, ceramic and glass tubes.
Yeah. I mean, I think that the ceramic ones are easy, they're less fragile, that's all. They cost a bit more. But it doesn't affect the performance as far as I understand. The thing that affects the performance is what kind of focus you get. If you get a micro focus and a line focus. And I'm not super expert on that, so it's best to work with the manufacturers to figure out what's best. But the ones that are giving the highest intensity are these micro focus. And they have a long line, and then what you do is you look at grazing incidence at the line. So you're getting X-rays from that whole long line, but you don't look at it this way on and get a broad beam. You look at it this way on, so it gets focused into like a very small spot. So there's very high intensities coming from these micro focus sources. Now, how do you monochromatize the incident beam? You want to have a single wavelength because you want a well-characterized single wavelength incident beam, and you're going to scatter it and then look at the wavelength afterwards. So, with these X-ray sources, you can actually make use of a very simple technique, which is using X-ray filter. So, an X-ray filter is just a piece of metal, which is a very calibrated thickness, and it's just an absorber. So you think, why would I put an absorbing material in the beam? Because it just makes my intensity of my X-rays less. But the reason is, if you pick the material of this filter correctly, it will actually preferentially absorb the X-rays that you don't want, and it will allow through the X-rays that you do want. So this is a nickel filter, and this is the what is this? This must be the transmission. So it's the inverse of the absorption. No, this is the absorption, I guess. So the absorption is high here. Yeah, this is wavelength going up. So this is energy going down. So energy going up is this way. So the absorption of nickel comes down and down and down with increasing energy here. But then you go through an absorption edge. This is where you're suddenly exciting a core level excitation. And so suddenly the absorption of this nickel jumps up like this. And if you use the right material, so nickel, I guess this is a copper spectrum, and this is a nickel filter, and the nickel absorption edge is just below the K alpha line here. And so you preferentially absorb all of this, and so you really strongly suppress this stuff, but you let the K alpha through. So the nickel filter just gives you a slightly more monochromatic beam. If you want a truly monochromatic beam, you have to put a monochromator in the beam, and this is a crystal. And you orient the crystal so that you satisfy the Bragg condition at some angle, and you put a slit to select that angle, and that will give you actually a monochromatic beam. So you place the slit at exactly the place where this wavelength here diffracts, so you get a truly monochromatic beam. I don't have a picture of that. So this lab equipment, you basically take a wallet full of rupees and you go and talk to the instrument manufacturer, and they'll deliver it and install it, and then you can start using it. They'll teach you how to use it. They're very anxious to sell you X-ray equipment. If you're very bold, you can build your own equipment. You have to be quite careful though, because X-rays are dangerous. So it's definitely preferred that you buy this, either some new or used version. But it will fit in your lab. You need a fair amount of power to run it, and you need water to cool it. So if you're doing powder diffraction in the lab, you would just call up Rigaku or Brooker, and they deliver your lab. But this is actually some beautiful work done recently where a powder diffractometer was actually put on the Mars rover and sent to Mars. And so what the geologists wanted to know is that you see this red sandy rock on Mars, and you say, what's it made of actually? So what you'd like to do is you'd like to do an experiment on the rock on Mars. So how do you do that? Well, how do we know what the moon is made of? So the way we know what the moon is made of is that actually astronauts went to the moon in 1969, 1970, 1971, and they bent down and they picked up rocks, and they put them in bags, and they sealed the bags, and then they came home and they brought the rocks with them. So those moon rocks are actually sitting at in Washington, D.C. in the Carnegie Institute or somewhere like that. But nobody's been to Mars and come back, so how do we figure out what the rocks are on Mars and what they're made of? So this Mars rover, this amazing machine, it's an unmanned machine, it was sent to Mars. And miraculously, what they actually did is they put an X-ray diffractometer on that machine. So there's actually an X-ray diffractometer sitting on the Mars rover. And it basically has a microfocus X-ray tube, and it has a very, very small power supply that can accelerate voltage and excite it. And then it has a pinhole collimator, and then there's a sample here, and then there's a 2D area detector, and then it beams back the diffraction patterns all the way back to Earth. So it's actually an amazing piece of technology.
It must be the only unmanned diffractometer in the universe.
Yeah, that's probably true, yeah. Well, you can build one here, you know, and then you don't have to have any grad students at all. You can.
Is it still working? Or?
That I don't know. I have a feeling probably not. I think maybe it's stopped working, but yeah. So this is actually a map of this white line here is the track that the Mars rover took, and each of these red dots is a place where it drilled a hole in Mars. So basically, a little arm comes out from the rover. It drills. It takes a core, and these are each of the holes that it made at all of the different places, Mojave, Big Sky, Greenhorn, and here they are, their location on this place. So this is the Gale crater on Mars where the rover was. Here it was sandy, so it didn't have to drill a hole, it just like scooped up. But the first step is actually drilling a core, so you've got a little core piece of rock. Then you have to, yeah, question?
Can you speak something about how are they cooling what is the cooling procedure in the Mars rover?
Oh, I have absolutely no idea, but that's a great question. I mean, it's actually pretty cold on Mars. So they may just have like very large kind of cooling plates, like the ears of elephants or something, right? That just, and there's essentially very little or no atmosphere on Mars. So if you have some very dark black surface that's kind of large area and you expose it to the sky, then the radiation is going to leave very rapidly. So I'm guessing, but I'm completely guessing. I have no idea. It's a great question. So after you've drilled the core, you actually have to pulverize the powder. You have to turn it into a powder, and I don't actually know how they do that either, because this is not my work. It's just like really cool. And then then you have to make a sample. So usually we have a grad student do that. You know, the grad student grinds the powder, and then they put it on a piece of paper, and then they scoop it up into a capillary, and they tap the capillary, and they do all this, right? So how are you going to do that remotely up on Mars with no grad student? So they actually have their sample holder they came up with in the end after many trial and error attempts was actually something that's kind of disc shaped. So it's like a little sachet here that's circular and shaped like a disc. And once they have the powder, they inject it. It gets injected into there. But what would normally happen is it would normally just settle down to the bottom. And it turns out that there's a very small amount of material, so when they expose this, they were getting very spotty powder patterns. They were very large number of spots and granule. It wasn't a good powder average. So what they actually figured out in the end was that you can use ultrasound. So what they do is the surface of this thing is flexible, so the windows of this sample holder is flexible, and then they beam ultrasound at it, and it causes the surface of this sample holder to kind of vibrate with a high frequency, and it causes the powder inside to kind of jump and dance like this. And so that does two things. It disperses the powder throughout the region, so the powder's kind of flying around inside. That's the first thing. And the second thing, you get much better orientational averaging because each powder grain is flying through the air and it's kind of rotating. So it's like very ingenious. It's a beautiful piece of science where people use their imagination and they came up with a creative solution. So you should all be encouraged to do this. I mean, think about how to solve problems and think a little bit out of the box. Like, if it's not just learning from an expert like me that you have to pack the powder into the capillary in such and such a way. I mean, if you can come up with some creative way of solving some problem, as long as it works, it's valid. And sometimes they can learn about the kind of geological history of Mars by seeing what it is. And you can see that this is the one that was found on Mars, and this is the one that was the control, and the quality is amazing. I mean, they're highly similar, basically. Okay, so that's enough about Mars. Let's come back to Earth. So the benefit of the lab source is that you have it locally available, and you can always use it. The limits are that you can't tune wavelength. That's not a huge limit if you have a good wavelength. But low flux, long measurements. The beam is highly divergent, which is not really necessarily a problem, but it's just adding to this kind of low flux that you're getting. So the experiments are slow, basically. So if you have access to a synchrotron, you want to use a synchrotron. So this is actually using the same physical principle as the lab source. In the lab source, at least in the Bremsstrahlung, what's happening is that you're accelerating or decelerating electrons. When they decelerate, when a charged particle accelerates or decelerates, it emits radiation. And so here the speed of the electrons is not changing. Firstly, you accelerate the electrons to very close to the speed of light, so much, much higher energy, actually basically gigavolts rather than kilovolts. And the speed of the electrons doesn't change, so they move around this ring. This is an evacuated ring. This is a very small synchrotron here, but they move around this evacuated ring at this very high speed, and they maintain constant speed. So you don't change the speed, but because it's going in a circle, you're constantly changing the direction of travel, and so you're applying an accelerating voltage, which is the centripetal force, the force it needs to bend the trajectory. So you're actually applying an acceleration, which is the rate of change of velocity, even though the electrons are staying constant speed. And so the amount of X-ray that's emitted depends on how sharp the turn is. So the original idea would be that you would have a synchrotron that was circular, and so then they would be emitting at every place because they're constantly moving, they're constantly being deviated. But then the amount of X-rays radiated is firstly going in every direction all around the ring, but secondly, it's not each little bend is not such a sharp bend, so there are less electrons coming off. So people said, okay, let's make our synchrotron to have this shape like this. We'll have straight sections. So we'll have straight sections like this, and then we'll have a bending magnet, and we'll try and make this bend a little bit sharper. So it's a straight section and then a sharp bend. So there's actually no radiation being produced in the straight section, but then you get a bending magnet here, and the radiation comes off here. Now, an accelerating particle will radiate electromagnetic radiation, and it radiates in 4 pi in the full solid angle, so in every direction. So if you just have a charged particle and you accelerate it, it will send a pulse of radiation out in every direction. But what happens here is because the velocity of the electrons is so high, they're relativistic. They're moving very close to the speed of light. And what happens is that the relativistic squeezing takes this fan of radiation, which is going in all 4 pi directions, and it squeezes it into a cone, which is in the direction of the velocity of the motion of the electron. So the electron is coming along this straight section. It goes through this bend. It's accelerated in this bend. It radiates. But because it's moving, its velocity is roughly in this direction. Actually, its velocity is kind of tangential to this curve. So right at the point where it's bent, it radiates a pulse of X-rays, and it's squeezed into a cone in the direction of travel. So you just simply put a hole in the shielding. You have to have shielding around here so that all of the grad students are not killed. That would be bad. So then you make a tiny hole in the shielding right at the right angle here, and you get this very intense, almost like a laser beam of X-rays coming out through that hole. And then the electron beam continues on into a straight section, and then another bending magnet, and another pulse of X-rays comes out here. So every time you have a bending magnet here, you have a pulse of X-rays coming out, and you can put an experiment down here. So you can have 1, 2, 3, 4, 5, 6, 7, 8 experiments going on at the same time at the synchrotron. So that's how they operate. And we have now at our new synchrotrons, we have like 30 beam lines, so 30 different scientific groups are working. And then It runs 24 hours a day for, I don't know, roughly 8 months of the year in different segments, and so there's plenty of access in principle to get to the beam. And so they open it up to a wide user community, and people can apply for beam time. So this is a bending magnet. It's a dipole. It just is basically a very strong magnetic field, and the magnetic field is up. And the right-hand rule means that you've got your electrons going this way, and the field is up, and so the accelerating voltage is in, and so the thing accelerates, and then the X-rays come out here, and they have a slight divergence. They have a slight fan because you have this continuous bend here. So the ones coming out at the beginning are in a different direction from the ones coming out at the end, and that's like a very simple thing. So people are very excited about this, and actually this experiments were parasitic. So the high energy physicists were using these electron beams to do high energy physics, and this synchrotron radiation was terrible for them because it was just sucking energy out of their beam. So they had to continually pump energy back into the beam just to keep it going. And it was only when materials scientists came along and said, hey, we can use that, just let us drill a hole in your shield wall, that it started becoming like useful instead of useless science. So we were very happy to have the X radiation from these bending magnets. But somebody realized that, hey, actually it's the bending of the beam that is producing the X-rays. And we were making use of the fact that you had to bend the beam in order to get it in a circle. But there's nothing to stop you putting magnets into the straight section which will wiggle the beam. So they invented the wiggler. So this is a wiggler. So what you do is, instead of having a pipe here, an empty pipe, you replace it with this thing. And a wiggler has a series of magnets where it has an up, down, up, down, up, down arrangement like that. And then when there's the up arrangement, the electron beam gets deviated that way. When there's the down, it comes back this way. Up, it goes back that way. Down, it goes. So now the average direction is still the same. It's still moving. On average, it's still moving in this direction. But because it's being wiggled like that, all the way along that straight section, it's actually emitting X-rays. And those X-rays are being squeezed in the forward scattering direction. And so now to make use of, you see, this hole on the bending magnet was at the tangent. It was at the tangent to the bend. What you do now is you make a hole in the shielding, which is not at the tangent of the bend, but it's actually in line with the straight section. So you can actually take energy from both the bending magnet and the wiggler, because you can have this hole that's at the straight section, and you can have another hole that's not shown here, but it would be in between, which would be getting the bending magnet radiation. So you can support even more experiments. And the radiation from this wiggler is a little bit like the radiation from the bending magnet, except that it's multiplied by the number of wiggles. So let's say each of these guys was a wiggle. There'd be 1, 2, 3, 4, 5. This is a 5-pole wiggler. The intensity from this wiggler would be 5 times the intensity from that bend magnet. In fact, it could be even higher, because you might be wiggling more sharply than the bending magnet. And so then people got greedy, and they said, okay, I'm going to have a 26-pole wiggler and get a 26 times enhancement, and so on and so forth. So this is the wiggler here, where you have the up and the down, and it just wiggles like that. And then you can have a multi-pole wiggler, which is many of these together. Something that you should see here is there's actually one of your straight sections, at least, has to have a RF cavity, radio frequency cavity, and this is how we actually accelerate the electron beam. So you take electrical pulses and you put them into these cavities. They create an electromagnetic field, which is kind of like a wave, and it's synchronized with the electrons coming through. So it's kind of like the electrons surf on these waves, and they get accelerated. So when the electrons go around the ring, they actually slow down a little bit, because they're losing energy at each of these places. Every time they emit some electromagnetic radiation, they're losing energy. And you need this RF cavity to then accelerate them back up so that they can make another journey around. So after being very excited about wigglers, somebody came up with the idea of an undulator. So what's the difference between an undulator and a wiggler? So this is a wiggler, and you can have a multipole wiggler, and the multipole wiggler kind of looks like the undulator. It has many, many wiggles in it. But you can actually tell a little bit from the name. So a wiggle and an undulator, and if you think what the word undulator means, it means a kind of a gentle undulation. It's kind of a gentle wiggle. And why would you want a gentle wiggle rather than a severe wiggle? You get more X-rays from a severe wiggle. But it turns out that you can actually tune this undulator to act coherently. So actually what you have is you have an electron beam moving through this undulator at a certain speed. So you know how much time it takes for the thing to get from one of these undulations to the next undulation. And you know that it's going to emit radiation at each of these places. And actually, if you're very careful in how you design it, you can make it so that the X-ray that's emitted here will be coherent with the X-ray that's emitted here and here and here. So it means that the wavelength and the phase of the X-rays are in tune, and so you get a coherent summing of these. It's making it even more like a laser. And so the wiggler radiation and also the bending magnet radiation gives you this nice broad continuous spectrum. But the radiation coming off of undulator looks like this. It's highly structured. It almost looks like Bragg peaks, basically. So you're basically getting the X-rays being produced by the undulator to be coherent. And then if you sit on one of these guys, so your monochromator, you want to select a wavelength which is exactly at this guy or exactly at this fundamental here, you get a massive enhancement in the intensity. So the undulators are giving really high intensity, and they're just amazing. We often use wigglers for PDF work, and the reason is that actually if you're interested in high energy, you get actually more intensity at high energy from the wigglers than you do from the undulators. So we can't actually make use of these undulators too much, but there are some PDF beamlines on undulators. ID11B, ID11B at ESR, at APS in Chicago is on an undulator.
What is the dimension of a wiggler and an undulator length?
Yeah, so the straight sections now are some number of meters. They're like 3 or 4 meters. So the length can be 3 or 4 meters. And the size of these things, the magnetic forces that you need to wiggle these relativistic electrons are very, very high. So the magnets are very strong, and they have to be built into these metal frames that are massive. So the size of the metal frame itself is like this, and it goes up and it goes over and it goes down, and it encases the whole thing. So the whole thing itself is probably, it's probably a modern undulator is it's almost as big as this wall like this, and they sit inside these rings.
Can you explain injector magnet that was shown?
Injector.
Injector magnet.
Where is it?
Yeah.
Injector magnet. Yeah. So what happens is that I told you that the beam loses energy, and we have to replace energy by this RF cavity. But the beam also loses its electrons. So it's flying around in a tube that's completely evacuated, but you never get rid of it all. You never get rid of every gas atom in that tube. So occasionally one of these electrons will hit a gas atom, and it'll be scattered out of the bunch, and it'll go crashing off into the sidewall of the tube. And so gradually over time, the current in the ring goes down and down and down. So you actually want to not only replace energy, but you want to replace electrons. And so we need a way to inject the electrons, but you can't just put a stationary electron in and have it this RF cavity is not going to, it's tuned to the speed that the main electrons are going. So you actually have another accelerating ring over here, and the accelerating ring, you inject a bunch of electrons into it at low energy, and you gradually ramp up the energy until it's basically close to the energy of this ring, and then you have to phase it right. So this pulse is coming around like this, and your pulse is coming around like this, and then you have a kicker magnet that this thing is going round and round in here, but you apply the kicker magnet that pushes the electron beam out of this ring, through this tube and into that ring, and then it joins into the bunch. So it's like amazing kind of technology of timing stuff. But yeah, that's what that does. If you're going to monochromatize with a crystal, you do it like this. So typically you only actually need one crystal, and the white beam comes in, and you satisfy the Bragg condition. I didn't talk about that yet, but you satisfy the Bragg condition at some angle of this detector, which depends on the wavelength. And so actually the white beam is going to diffract at all from these set of planes. It's going to diffract at a range of angles. So actually X-rays are going to come off the crystal in some fan like this. And to select a particular wavelength, you want to just take that fan and put a slit in it at some position. So some physical position will select you a wavelength. Now the problem with single bounce monochromators at synchrotrons is that your beam comes in here, you have a crystal, and your outgoing beam is at some angle like that. And you want everything in the synchrotron to be kind of going in a straight line. So what we do is we have it bounce off a first crystal, and at some fixed angle with respect to the first crystal, we have a second crystal, which is also at the Bragg condition, and the selected wavelength bounces off the second one, and it goes straight like this. And so you can see we have this nice straight geometry where the beam has been displaced vertically, but it's still moving in the same direction. This also gives a much cleaner beam, because this first crystal here, it's getting the full white beam from the synchrotron. So there's a huge amount of energy in a very small space here. And so this crystal here, number one, this crystal has to be cooled. So there has to be either water flowing through it. More commonly these days, it's cooled with liquid nitrogen. So you have to drill holes in this crystal and pump liquid nitrogen through it, otherwise the crystal will be destroyed by the white beam. Now, when the white beam hits that crystal, it goes from being cool to being hot. So it changes its temperature, and that distorts it. The lattice planes, there's thermal expansion, and there's stuff that goes on. So when the white beam switches onto here, you have to actually wait for this thing to stabilize. But it also produces distortions in the crystal, which produces a kind of a slightly dirty, non-monochromatic beam. But this second crystal here is also at the Bragg condition, and it's never seeing the white beam. So this crystal doesn't have a very high heat load on it, and so this one doesn't get distorted, and so the beam coming off that second crystal is much cleaner. So this double bounce monochromator was actually quite revolutionary when it was invented. So the beam goes through, it hits your sample, then it has to be detected. The most simple way of doing it is with a point detector. More fancy is to have a 1D detector. Now for PDF measurements, we need to detect short wavelength X-rays, and that's actually a bit of a challenge. Let me see, I'll come back to that. Most common kind of point detector that's used is actually scintillation detector. It works like this. So you actually have this scintillator material, which is something like thallium-doped sodium iodide. And the thallium is very high. It's highly absorbing because it's a very heavy metal. And it actually produces, when it's photoexcited and it's embedded in a sodium iodide crystal, it actually produces optical phonons, so its response is to emit light. So that's why it's called a scintillator. In principle, you can actually see, when the X-ray hits this material, you would actually see light. But we don't really want to see light because we don't want the light coming out the front of the detector. So what we do is we actually have a photocathode on the back. So this is a little thing that's sensitive to light, sensitive to visible light. And so this light that comes from the scintillator goes through to the photocathode. And then there's actually, this is using the photoelectric effect. So the light is actually above the work function of that material and emits an electron. The electron is accelerated by this field, and then it goes into these plates. And each of these plates is at a higher voltage than the other plate. So it bounces off that plate, and that produces this is a photomultiplier tube, so it's doing amplification. So it's taking a very small number of electrons that came from this process, and it hits the second one, and there are more electrons, more. So it just gives an amplification of the signal. And then out here, you actually can measure the current, measure the amount of electrons coming out. So this is a kind of very simple device. It's been around for many, many years. It works rather well. So this is how the point detectors work. I don't think I have a line detector. This is a line detector or a 1D detector, and it's a curved one because it has a very high angle. And the way that these work is slightly different. They're basically gas detectors, and they have either a wire or a metal blade inside, which is at a very high voltage, and it's sitting inside gas. And the X-rays go into the gas, and they ionize the gas, kind of like lightning. It's like a lightning strike. And then because you have this very high voltage wire inside, the ionized gas will be either attracted or repelled from that. But if they're attracted, then they'll come to it, and you then get this pulse of current that comes out, and then you put it through pulse shaping electronics, which also has amplification step. And so this is actually a photon counting detector. It counts individual photon events. So if a single X-ray comes in, you get a single pulse of current, and you say, I detected an X-ray. And this gives you some energy resolution because the size of the pulse depends on how energetic the X-ray was. And you can use electronics to gate it. So you can say, I only want to accept pulses that are above this lower threshold and below this upper threshold. And these are the pulses that I know have the energy of my incident X-rays. So you gate it, so it will, any pulses that come that are from some different energy process, it will ignore it, but it will only accept the ones that are coming with your incident energy. So these are very nice detectors, actually. These are better than the scintillators, except that it's very easy to take a scintillator and turn it into a large area 2D detector. So the detectors that we're using mostly right now are the synchrotrons, are these very large area 2D detectors, and they're basically working on this scintillator technology. So they have a scintillator on the front, and then behind that they have an array, something like 2,000 by 2,000 little patterned electronic chips underneath, and the light goes through to each chip. So you're actually, this thing is basically pixelated with all of these. It's not using now this photomultiplier tube, which is a big thing. It's doing the gaining electronically, but it has chips on the backside. So these things now are very large. They're like 300 or 400 millimeters, so almost half a meter on each side. So these detectors have essentially revolutionized how we do PDF in this rapid acquisition mode. But the downside of these detectors is that they are integrating detectors. So basically what happens is X-rays come in, and they basically leave some kind of defect there. Defects are left all over the place, and then the defects are kind of read out afterwards. You can't discriminate. You're just basically, energy is being dumped into the detector, and you're collecting all the energy, so you don't really know what energy the X-ray was that came. So what we would really love to have is actually photon counting detector, which is a similar technology to this in a 2D format. But it has to also be efficient for stopping hard X-rays. And hard X-rays are very penetrating. And new detectors are just appearing right now. So there's a detector called Pilatus, which has this photon counting technology. And it's using cadmium telluride material to actually collect the charge. And this is a high atomic number, high Z material, so it's good for hard X-rays. So we're getting very good efficiency and photon counting detector. And it's being built into devices that are this big. And they currently cost somewhere between $5 and $10 million for one device. But the price will come down. And the quality of the data we're getting from those Pilatus detectors is just amazing. There's just as we've had a revolution in the sensitivity that I told you about, we're going to have another revolution almost the same in sensitivity when we get these new detectors. Okay, so here are some synchrotrons. This is the APS in Chicago. Before I showed you NSLS2 at Brookhaven. This is a beautiful picture of Grenoble in France. This is the ESRF. If you ever get a chance to go there, you should. It's beautiful. You can go skiing up there. These are two rivers that come together right down here. And if you go rowing like I do, you can go rowing down here. And there's the synchrotron right there. And then ESRF is next to ILL. ILL is a neutron source I'll tell you about later. That sits right there. So on this campus, you've got one of the most powerful neutron research reactors and one of the most powerful synchrotrons. And you just have to be able to speak French. Actually, you don't have to speak French. They speak English there. And this one, I'm not sure, is maybe Spring 8 in Japan. This was Kirsten's slide, so I don't know. So this is, I don't know how old this is, but this is where all the synchrotrons are in the world. And you can see everywhere except Africa has a synchrotron. So there's actually a project right now to try and build some kind of synchrotron in Africa, because it seems a shame that this one's all grey. You have one in India, but it's a very low energy synchrotron. You can't do PDF work there. In fact, you can't even do X-ray diffraction, basically. It's kind of, is it infrared or?
We have a 2.2 GeV synchrotron also.
You do?
Indus 1 is 450
yeah.
MeV, and that Indus 2 is 2.2 GeV.
Oh, it is?
So you can do hard X-ray with that.
Okay, yeah. So the original NSLS was 2.5 GeV, so that's the same energy as. So I don't know anything about that. Yeah, that would be interesting then to find out more. Maybe there's a.
Still not running at that level.
Oh. So yeah, we should talk about that. So we should discuss. Yeah, we should discuss offline about that. But again, I want to emphasize that there are ways that you can actually get access to these other synchrotrons. And if you can't afford to travel to do the experiments, you have to solve that problem. But again, there's these mail-in programs, and there's also collaborators. Local collaborators is a good way to go.
APS is the most powerful synchrotron in US.
So NSLS2 is the most brilliant. It has the highest brilliance. So that's the new synchrotron at Brookhaven. And APS has the most flux at high energy. So they have different characteristics. And they're working on an APS upgrade which will have, which will surpass NSLS2 in both flux and coherence. But that's 10 years away. These are the synchrotrons in Europe. So this was Kirsten's slide. So she's a Dutch lady, a Danish lady, I mean. And she's very proud of MAX 4 because MAX 4 is actually in Sweden. And it's actually quite a small synchrotron, but it's also very, very high brilliance. So another breakthrough they had in synchrotron technology was coming up with a special design for the matrix that gives you very, very low emittance, which means that the electron beam's very tight and the source size is very small. And so even with these latest generation smaller synchrotrons, you can get extremely good performance. And this is some I don't know, Prime Minister of Denmark opening it. And look, they even put him to work putting some shielding in place. So that's good. Finally a politician doing something useful. This is a little bit what a beamline looks like. I think it's maybe that Max 4 beamline, but the ring is kind of going around here, then there's the hole in the shield wall here, and the X-rays come out in a straight line. And because there's so much radiation that it would kill anything in its vicinity, what we do is we make these lead boxes, and we call them hutches, and they're so big that you can walk inside them. So when the beam, you close the shutter so the beam is off, you walk inside the hutch, you do your work, you walk outside the hutch, you close the door, then you open the shutter. And you have the optics cabin. This is where the monochromator is, and there's a lot of scattering that comes off the monochromator that you don't want interfering with your experiment. So you separate that into a separate hutch. And then you have the experiment cabin. This is where your sample is and your detector. And you have a shutter here and you have a shutter here. So you can work in this hutch even when this one is closed. And then you put your sample here, and then you walk out, you close the door, you open the shutter, and you come over here, which is the control cabin, where you actually have a computer, and you can start controlling the machine with the computer. So because everything is remote in the hutch, it all has to be motorized and under computer control. So it's a massive operation to get these things built. But once they're built, they work really well. And they're fun to use. So we go here, typically we'll have 4 days at the beam line, and it runs 24 hours a day for 4 days. And so I send my students and we work in shifts. So one group is working, the other group is sleeping, and then this group comes in and works, and this group sleeps. This is kind of how we do it, but it's really kind of fun and exciting because things go wrong and you have to fix them, and you have to fix them quickly because you're running out of beam time. So it's a lot of fun. So I think I mentioned about this. This was actually the setup at NSLS2 when we first did the rapid acquisition PDF. And the sample here, the monochromatic beam, and then the 2D detector. So this is the rapid acquisition setup. It looks like that. Okay, synchrotron beamlines for PDF work. The students will get the copy of the slides, right? I'll have to make them. If I make PDF copies, you can give it to the students. Yes, I mean, you can use this as a reference here, but this changes with time, but it's helpful to know which beamlines are good for PDF work, because when you go to the website of these facilities, there's 30 beamlines and you don't know which one you want, and it's really hard to figure it out. So this is actually a little crib here to help you, and you can go to the web pages of the facilities and you can look for these beamlines, and this is where you can find more information how to use them. Okay, so I'm going to move on to data processing. I don't know what you want to do. I have also neutrons to talk about. So the schedule was like 9:15.
We can have a break and then continue, or if you want to continue.
I mean, I'm okay. Depends if people need a break or not. What about tea? Is there tea? No tea.
Tea is at 11:15.
Okay, yeah, so we're good. Okay, everyone can get up and stretch.
Or maybe we can have a introduction of the participants.
Yeah, sure.
You can tell your name and institute. Very brief introduction.
Yes. So I'm PSR Krishna from SSPD BRC, Solid State Physics Division BRC, and basically we run a national facility for neutron scattering, and I man two of the instruments, two refractometers. One of them is for PDF, but up to only 15 astrometers. So
Myself, Manjeet Singh. I am working in a college, university college in Kanpur. It's a rural college. I am working there as associate professor in the Department of Physics. So I was interested in knowing the things that are going on nowadays. That is why I attended this course. Otherwise, I am not related with this research work. I simply had interest in solid physics because I am teaching this for the last 5 or 6 years, solid physics. So this course was on crystallography. That is why I wanted to know something related to this. Thank you.
Myself is Anshul. I am working in this university, GNDU University, as a junior research fellow, and I am working with the structures of multi-toroid perovskite structure. So this work is for a great interest for me. Myself, working head research fellow in the guidance of Professor Ketan Singh. I am working on magnetic materials for working management.
I am Yogesh, and from this university I am working on amorphous materials like glasses.
Myself Nubur, and I'm a research scholar at the Department of Physics, GNDU, and I'm working under the guidance of Dr. Atul Khanna on amorphous, basically telluride glasses.
Myself Priyanka. I have completed MSc from this university.
I'm Shankar Dutt. I'm the second year master student in the Department of Physics, Guru Nanak Dev University.
I'm Hina Verma. I'm a student of this university, Department of Physics.
Myself, Arjun Batra, from the same university. I'm a MSc student in the physics department. Myself, Parasay. I'm also an MSc student from this university, and I'm interested in scattering.
Myself Surojwala from Kuchedar University. I am working on biosciences.
My name is Harpreet Singh. I am a research fellow in GNDU University, Patiala. My working area is nanoparticle.
I'm Siddharth Kumar from IISc Bangalore. I'm mainly working in transition metal oxides.
Hi, myself Anand Patel. I am also from IISc Bangalore, and I am doing my PhD first year under Simanta sir, and I am working on ultra thin film growth.
Myself Subhash, I am from Kucheta University, and my research work in conducting polymers.
I'm Manmeet. I'm doing my BSc from this university.
Hi, my name is myself Supriya Deepkar, and I am doing the BSc Honor Physics in this university.
My name is Prabha Singh. I am from IIT BHU, and I work on multi-toroid perovskite solid solutions.
I am Anupam Singh from IIT BHU Varanasi. I am currently working in the field of intermetallic alloy in the supervision of Professor D. Pandey and Dr. Sanjay.
Myself, Amandeep Kaur, doing PhD under the supervision of Dr. Kidana, and I am doing research on oxide glasses.
My name is Jinder Kaur, and I am research fellow under the guidance of Dr. Atul Khanna, and my topic of research is glasses.
My name is Amarjit Kaur, and I am doing PhD under the supervision of Dr. Atul Khanna, and I am working on board telluride glasses.
Hello sir, I am Priti. I am a research scholar from this university, and my working area is DMS material and conducting oxides.
Hello sir, I am Anumi, and I am working here as a research scholar, and I am working in the field of multiplex.
My name is Orko, and I am registered at Jawaharlal Nehru University. I am working in metals and solution at IUCA, India University Center, and yesterday we had some discussion. I am working on cadmium oxide, oxide-based material, and its test transformation.
Myself, Seema Thakur. I am a research scholar in this university and working on amorphous glasses.
I am Nilip Singh, research scholar from chemistry department, and doing research in the field of ionic liquids and nanoparticles.
Hello, my name is Komal, and I am a research scholar in the Department of Chemistry, and my research topic is nanoparticles. So I'm looking for working in the cold temperature.
Hello sir, I am
understand the structure.
Hello everybody, myself Jessica. I am working as VDC Media on ion incarnation effects on semiconducting nanomaterials.
Myself Shelja, I am research scholar and working on biology.
Hello sir, my name is Vikas Singh. I am working in field of single crystal X-ray crystallography.
And my people contributors are body testing and I am working on thermal semiconductor analysis.
Thank you.
That's good. Yeah. You want me to continue? Well, I'll just continue and I have a lot to get through. So.
Sir, we have one question. You have designed this PDF UGI for GUI for Windows platform. Why not you have designed that for Android or more user-friendly? It's only available for Windows.
Which one?
The PDF GUI software. It's not available on Android platform.
Well, it's available on Linux and Mac. But what do you want it? You want it on cell phone?
Yes, yes.
He wants it on Android.
Android version.
We are more user-friendly, more...
So I can give some exciting news, but you have to wait. Yeah.
For tablets or for this?
Yeah, so we're actually...
charge or these wires are like this. You can install this.
No, this is a great suggestion. So what we're actually working on is to take all of our PDF software and put it in the cloud. So actually it will be running on highly parallel machines somewhere, either at Columbia or even on Amazon. And so we have actually this thing running at Columbia. We've got an Amazon EC2 instance, so we've got an instance on the Amazon cloud, and we're running our PDF software. And we're going to actually develop browser-based GUIs, and then you will have your wish.
Yes, some simple application of JSON can also be there for this.
Yeah.
You can do this. It will be very user-friendly.
But we need help. Do you do GUI programming? Okay, so we've talked about how you make X-rays, and then we've talked about how you do PDF experiments with X-rays. And now we have to figure out a little bit about how to do the data processing. So the experiment looked like this, where the beam came in, hit the sample, and we exposed the detector. And actually, you have to go all the way back. But what the data looked like on the detector is this. So when we have a 2D detector, the data look like this. So what's happening is that as a function of position on the detector, that's actually the same as 2 theta in a powder pattern. And so if I just took a cut all the way up here, then there would be like no peak, and then a small peak, and then an even smaller peak, and then a bigger peak, and a small peak, big peak. So if I took a cut through here, I would get what would look like a 1D powder pattern. But because the powder is isotropically scattering, it's scattering in all directions, it's very inefficient just to have all of this intensity here, but just take a cut. So the first step that we do is we actually have software that will do an azimuthal integration. So we'll move out to some value of 2 theta, and then we'll integrate all the intensity around the ring at that constant 2 theta. And then we'll move to another value of 2 theta, and we'll integrate all around the ring at that value of 2 theta, and we move out, and we get a continuous one-dimensional diffraction pattern where we've actually integrated these rings all the way around. So that's the first step. So we go from, if we have a 2D, if you have a point detector, you don't have to do that step. But if you're working with a 2D detector, you have to do that step. And the result of that is a one-dimensional pattern. So one-dimensional diffraction pattern is the raw, is what I'm calling the raw data now. But we still have to process the raw data to get a PDF. Now, the raw data has in it the coherent scattering, and the coherent scattering is the part that contains the structural information. So the coherent scattering is the part that we want. But the problem that we have is that there's all these other experimental aberrations that are also affecting the data that we have to correct for. So there may be an incoherent scattering contribution. So this is like a constant or very slowly varying background that contains no signal at all because it came from incoherent scattering. So it's just like a constant background that lifts the whole intensity up. There are also different backgrounds, and you have to think what the sources of those backgrounds are, but that's basically parasitic scattering. That's scattering that's appearing in your diffraction pattern that's not coming from your sample. So some examples of that are air scattering. The incident beam is actually flying through air before it gets to your sample, and it's flying through air after it goes through the sample. And the X-rays will scatter off air atoms, and then it will produce intensity that will be spread over the whole detector, but that's coming not from our sample but from air. So that's a source of background. Another source of background is that we typically load our sample into a holder. So we put the powder into a capillary. The capillary is either made of glass or it's made of some plastic like Kapton. And so some scattering will appear in our pattern which is coming from the sample holder, not from the sample itself. So there are different sources of backgrounds. There can also be secondary scattering. So an example of secondary scattering is that let's say there's some X-rays that were scattered off a slit up here, and then they go up here and then they scatter off this thing, and then they scatter into our detector. So X-rays can get into your detector from all over the place, and we have very high energy X-rays, and they're not very strongly absorbed. Neutrons is a similar problem. Neutrons will get into your detectors from everywhere. So these are backgrounds that have to be subtracted. There's also multiple scattering. So the equations that we use to obtain the PDF, this Fourier transform, it assumes that only one scattering event happened in the sample. So this is a good approximation if your sample is weakly scattering. And so if we make the sample small, and we know that X-rays are weakly scattering, the highest probability is that the X-ray will go through without being scattered. The second highest probability is that the X-ray will go through and it will have one scattering event. And that's like an order of magnitude down, or some orders of magnitude down. The next highest probability is that it will go through, it will be scattered once in the sample, but it will get scattered a second time in the sample before it comes out. And then there's every order of that. There's three times multiple scattering, 4 times multiple scattering. The probabilities of all of these things goes down and down and down. Sometimes we neglect multiple scattering. Sometimes we don't neglect it. Sometimes we have to correct for it if it's significant. So these are all, we call it parasitic scattering. It's different contributions to the signal that's coming not necessarily from our coherent scattering that we're interested in. And all of the intensities can be modulated by multiplicative corrections. So these are additive contributions, and these are multiplicative contributions. And so the easiest one to think about is absorption. So actually, X-rays get absorbed by material. That's why if you take an X-ray of your body, you can see the bones. And that's because the bones are more dense. So the X-rays are more absorbed in the bones, and so they appear darker on the film. So that absorption is happening in all samples, and it's happening when we do our experiments. And so it's reducing the intensity of the outcoming X-rays, and the amount of absorption depends on the path length through the sample. So it's quite a complicated correction where we have to figure out all the possible path lengths through the sample and then correct for the absorption. Polarization is also an issue. So the X-rays have some polarization. It's an electromagnetic wave. It's propagating in this direction. And what it is it's an oscillating electric field and an oscillating orthogonal magnetic field. So if you just consider the electric field modulation, it's actually oscillating in some direction around the direction of travel of the beam. So it might be oscillating up and down the electric field like this, or it might be oscillating horizontally, or it might be oscillating at any angle. Now, if you have an unpolarized incident beam, it's actually oscillating in every direction with equal probability. But if you have a polarized incident beam, you select one direction where the electric field is oscillating. So that's called a polarized beam. Now, we have to do a polarization correction because you scatter off your sample at some angle, and it turns out that actually, depending on the polarization state of your incident beam, the intensity you get at that angle is modified. And basically what it is if the electric field is oscillating in some direction, you're looking at it from some other direction, you take a projection of that. So if I'm looking at it from this angle and it's oscillating vertically like this, I'll see the whole intensity. But if it's oscillating horizontally, I'm looking along the direction of oscillation, I see no intensity. So just from this polarization, full intensity, to that polarization, no intensity. So that's the polarization correction. And so we have to correct the intensities for that. And for our 2D detectors, what it means is that actually the incident beam in the synchrotron is actually horizontally polarized. So it's polarized in the plane of the beam. So this is the horizontal plane, this is the vertical plane, and the synchrotron is actually polarized, the synchrotron beam is polarized this way. And so we get a higher intensity up here than we get down here for the same ring. So if you plot the intensity around this ring, it has this beautiful fourfold pattern like that. And we correct for that fourfold oscillation, that's the polarization correction. Now, the corrections, there are very many corrections, and it's a very detailed subject. And so in my book, there's chapter 5. And chapter 5 in my book is 100 pages long. And all that chapter 5 it deals with is doing these corrections. So this has been a huge headache over many, many years, but we actually know how to do it. And you don't really need to know these as sample volume effects, incident flux for now. But you know the detailed mathematics and everything is in that chapter of the book.
The book is
underneath the Bragg peaks. Underneath the Bragg peaks, yeah. So basically, I wrote that whole chapter. Takeshi didn't. My advisor, my colleague, co-author, didn't write that chapter at all. He was very lazy, and it took me a long time to write it. And in the end, when I was writing the first edition of the book, my kids, so you all met Sophie yesterday, she's 19, but she was 3 years old when I wrote that chapter. And then when kids are 3 years old, they're running around and they're causing disturbance and you can't concentrate on anything. So I actually had to send Sophie away. So I sent her away with her sister and her brother and her mother, my wife, Debbie. And we were in Italy. I was on sabbatical, we were working in Italy. And I sent them to Egypt. And so they went to a resort in Egypt by themselves, and I just spent the whole time back in Rome finishing up chapter 5 of that stupid book. So anyway, I can go through some of these a little bit. I don't want to go too slowly. But I've already mentioned about this. The absorption correction depends on the X-ray energy. It depends on the elements present, so you need to know what your sample is made of, and you need to tell that to the program. It depends on the path of the X-rays through the sample. So our program that does the full corrections is called PDF GetX2. And so you can correct you have to tell it the geometry, whether it's a capillary geometry, flat plate geometry, transmission geometry, and so on. The multiple scattering, I told you what that effect, but it can be quite large, and we basically correct it by taking the sample and dividing it into tiny volume elements and then assuming some scattering probability in each element and then tracing the particles through. There is in the end a normalization, so one normalization is for the incident beam. So obviously you get more intensity if you have a higher incident beam, so you divide by the incident flux. there's a normalization for the angle-dependent change of the illuminated sample volume. So if you have a capillary geometry, the amount of sample illuminated doesn't depend on angle, so it's a very nice symmetry. But if you have a flat plate geometry and you're doing symmetric flat plate, when you're at high angle doing backscattering, your beam size on the sample is almost the same size as your beam cross section. But when you're at glancing angle, at low angle, your beam size on the sample is much larger than your sample cross section. So the actual geometry, the amount of your sample that's illuminated by the beam, changes with angle. So this is another correction that we have to do. And the final normalization is that we have this condition that as q goes to infinity, S of q goes to 1. And so that's basically what we use to figure out how much sample was in the beam. So in principle, if we know the density of our sample, we can get this absolutely, but normally we do it by trial and error. With X-rays, Compton scattering is inelastic incoherent scattering. So this is a quantum mechanical effect. It's that actually some X-rays will come in and they'll hit an electron and they'll bounce at some angle, and the electron that they hit will recoil, and so it will actually take away a little bit of energy and it will change the momentum of the sample. But this process is incoherent. So this is one of the incoherent sources of the beam. We calculate it theoretically. Parasitic scattering in the backgrounds I told you about. Polarization correction I told you about. If you have a photon counting detector, you have to worry about dead time. So remember, with the photon counting detector, the X-ray came in, it ionized the gas got attracted to the high voltage wire, it produced a pulse of current, that went down the wire, it went into the pulse shaping electronics, and then it came out as a count in your counting program. That process all takes some time. It's actually rapid, so it takes microseconds, but it does take microseconds, and so during that period of time your detector is dead. So if another photon arrives during that period of time, that photon won't be counted, and that will actually affect the measured intensity. So your Bragg peaks are very high intensity. It means the photons are coming very fast at those angles, which means that proportionally more of the photons are not being counted because of this dead time problem. So this is a kind of a correction which depends on the intensity. So the best way to deal with dead time is to actually not saturate your detector, not put too much intensity onto your detector. But then if you don't put much intensity on your detector, you slow down your whole measurement. So one thing we do is we make a compromise. We allow some dead time to occur, but we predict what that dead time will be because we know how much time it takes the detector to recover. So we know the detector dead time, and we predict what the number of photons that probably arrive during the dead time. So that's a theoretical correction that we do. There's also a calibration that you have to do, which is that if you're measuring with the point detector, you know the 2 theta angle, so you know the angle that the detector made, but you don't know what the Q value is. So Q is this momentum transfer variable that we use. So we have to do the 2 theta to Q conversion. And when we're using a 2D detector, it's not even 2 theta versus Q. It's actually the address it's the pixel address on the detector, which is a linear geometric value. So we have to do that conversion from pixel coordinate to Q. This needs to be done very accurately. And the way that we do it is that we measure samples where we know very well the lattice parameter. And then we make a kind of a calibration map so that pattern is correctly determined. And then we don't change anything. We don't touch anything. And then we do the experiment again with our sample, and we assume that actually when we measured our sample that the calibration didn't change, and that's a good assumption. All right, so you don't have to read chapter 5 of my book. I recommend actually you don't, unless you're having trouble falling asleep and you need help. Because all of these corrections have actually been incorporated into these programs. I mean, it does actually help if you know a little bit about the corrections, so you know what absorption is and what multiple scattering is and so on. But our program, which is very widely used, it has a GUI, is PDF-GetX2, and it implements all of those corrections. Then there's also a very good program from Alan Soper, who's at ISIS in the UK, that's GoodRunX. Valerie Petkov's program, RAD, is also available, but I think it's actually less good than either of these two. We now have a new program, PDF-GetX3, which is the one that we're going to play with today, and I'm going to just describe it to you briefly. And there may be others, but I think these are the main ones. And these are all free software that you can download. So with PDF-GetX3, what we did is we said, okay, a big impediment to doing PDF is all of these terrible corrections. Like, it's really easy to do read-felt refinement because you get the data off the instrument and you're processing it immediately. But people were having trouble adopting PDF because it seemed like you had to do all these corrections that were difficult. And there's my chapter 5, which is 100 pages. It's like this huge, big hassle. So what we said is, actually, when we used PDF-GetX2, we actually had this secret button inside the program that we didn't tell users about, which actually did an optimization. So basically what it did is there's a few parameters inside PDF-GetX2, such as the density of the sample and the absorption correction, things like this. And when you use PDF-GetX2, you have to adjust the values of different things in the program until you get the right normalization, because we don't know the density correctly. So we had this secret button where the program would actually automatically find the right normalization by tweaking these numbers a bit. And so I had the idea that maybe we don't need to do these corrections at all. Like, maybe we can do a completely ad hoc correction where we just use that button and we don't even tell anyone about corrections. So the multiplicative corrections we still have to do, like the multiple scattering, but all of the additive corrections we can take care of automatically. So the question was, is it possible to obtain a reliable PDF from the raw data doing a completely ad hoc correction, but knowing the asymptotic behavior of the S of Q and the properties of the PDF itself? So there's some things that we know about these things. So we know that S of Q asymptotes to 1 as Q goes to infinity. We know that. And we know that S of Q function asymptotes to minus B average squared as Q goes to 0. So we know the asymptotic behavior of this function at each end.
What is the B average?
This is the scattering length. So this is in neutron language. Yeah, so Siva knows, but that's like the atomic number for X-rays.
For that, it will be the Z.
The Z, yeah, the Z. It would be the Z averaged over the whole sample. The other thing that we know is that in the PDF, there's no peaks until the first peak. The first peak is the nearest neighbor peak between two atoms. Right? There's no peak shorter distance than the nearest neighbor distance. And if you remember, the relationship in the Fourier transform is that the position in real space is like a frequency in reciprocal space. And so the low R region corresponds to a low frequency in the Fourier space. So what we know is that actually there's no Fourier component in our signal from the sample that has a wavelength longer than 2 pi over R nearest neighbor. So this is the separation of the nearest neighbor atoms. There's no any change in the intensity which is oscillating or undulating with a frequency lower than that is coming from background or coming from some other source. It's not coming from the sample. And so what we can do is we can actually fit polynomial functions to the data as long as we ensure that no frequency can be in that fit, which is higher than that. So that's the whole basis for PDF-GetX3. These are the equations that we worked out, and this is Pavel's paper, Pavel Juhas. So we basically say that the measured intensity is equal to the intensity that we're after times a multiplicative correction and an additive correction. This is always true. When we do all the corrections explicitly, we try and evaluate this, and we evaluate this perfectly. What we're assuming now is that we don't know this and we don't know that. And then what we do is this beta, which is the kind of the inverse of that. This one we correct for, but this one we assume is just arbitrary, and then we build it in. So the f of q that we're after is q times s of q minus 1, but it has this unknown background term in it. So we expand that out and we get this. And then we invert it, so the coherent f of q, which is the one we're after, is this measured one minus this q times this p. And this thing here is basically a polynomial fit to the data. So this is brutal. What we've done is we've taken 100 pages of well-characterized corrections, and we've said we can correct it all basically by fitting the data with the polynomial and then removing the polynomial, as long as we satisfy these conditions. So let's see how well we did. So we benchmarked it against PDF GetX2, and this is nickel, this is barium titanate, and this is a cadmium selenide nanoparticle. And the green is PDF GetX3, the new brutal method. And the blue is PDF GetX2 with all the corrections done perfectly. And the red is the difference curve. And the dashed line is just kind of like a guide to the eye. But you can see that they basically give, with exceptionally good fidelity, the same PDF. So we're really confident that PDF GetX3 is actually working just as well as PDF GetX2. And the nice thing about it is that we can do the data correction in microseconds. So actually we can do the correction. We have you'll see it when we do the hands-on demo, there's a slider, and you can move the slider, and the slider changes some of the parameters in the program, and it's basically recomputing the PDF in real time as you're running the slider. That's how quickly we can do the PDF correction now. So this is also having a big impact because it just makes PDF easier to use.
It also doesn't require atomic number density.
Yeah, we don't need that anymore. So there's one drawback with it, and it will affect glasses people. So you need to be a little careful. And that is that because we do this ad hoc correction and we remove the polynomial fit, we can't actually guarantee that you'll get the data on an absolute scale. So if you want to take the first peak of the PDF and integrate it to get coordination number, that number is unreliable. If you have a series of data, what we found is if you have a series of data sets and you run them all through PDF GetX3, then the comparison between them will be reliable. As long as those samples were kind of similar to each other. Yeah, but so for glasses it's slightly problematic. But I also think that if you use the old programs, it's slightly problematic too, because the last step with the old programs was always basically doing some ad hoc corrections anyway.
Is there any provision to give atomic number density to get more reliable PDFs?
Well, not using this ad hoc approach, because we at the very end what we do is we yeah, I mean what we find is that we actually get quite good scale factors if you have very strong scattering. I showed you these very dilute systems where we're subtracting a small signal from a large background, and in that case the scale factor can be really arbitrary. But if you have a strong scattering and a low background, you get quite reliable scale factors. We haven't spent a lot of time looking at that. I mean, if it's of interest to you and the glass community, we could do some tests. I mean, this is how we do tests. So actually, I have to be clear, like one thing we did to get this overlay is that we allow the PDF GetX3 to rescale. So there's one parameter, the scale factor, and we vary that until we get this agreement. So yeah, the scale factor is, we need to do more work to find out when it's reliable and when it's not for the glasses community. When we're fitting models, it doesn't matter because one of the parameters in your model fit is scale factor. So it's very robustly taken care of. Okay. All right, that's it for X-rays. I have neutrons, but that can be after T, right?
Yeah, T is, I think, now.
Yeah. Does anyone have questions, actually?
So please feel free to ask any question.
Yeah.
How to get reliable coordination number from the PDF GUI?
Yeah, the coordination number.
PDF GUI. For PDF GUI, you have a structural model, and it will automatically give it to you. But you're interested in glasses, right? So we have to actually discuss how to use PDF GUI to model glasses. It's a little tricky. It's a slightly different problem. So the way that people usually get coordination numbers is you actually take the raw data and you integrate the first few. And that's certainly possible if you've done a proper normalization of your data. You don't need PDF GUI. If you have PDF GUI, you're putting a model in, and you're building into the model that coordination number, right? And that can be a variable. So there's a thing called occupancy factor, which allows that number to vary, and that's a refinable parameter. So you could get that number out, but it implies that the model you've produced is good. Otherwise, you'll get some wrong number out. We can talk some more.
Simon, the term pair distribution function and total correlation function, they are same things?
So total scattering refers to this concept where you take Bragg scattering and diffuse scattering, and you measure over the whole reciprocal space. So that's why it's total scattering. We're taking all the scattering. We're taking the Bragg contribution, the diffuse contribution, and we're not only that, we're measuring it over the entire reciprocal space. So it's total scattering. PDF is what you get if you take the total scattering intensity and Fourier transform it to real space. But in principle...
But he is asking, there is some confusion.
Oh.
The P of R, which is given,
yeah,
which is nothing but 4 pi R rho G of R.
Yeah.
Okay, so that and this capital G of R, they are related. There is no...
Oh, you're talking about there's different correlation functions.
Different correlation
functions. Yeah, there's a whole...
there's
a whole zoology of different functions, and actually some of the same functions have used different letters between the European and the US school. And there's actually a very good paper by Dave Keane in Journal of Applied Crystallography, which actually goes through these, and a lot of them are also in my book. But basically, the difference is like one function will be divided by the density, another one not divided by the density. Another function will be subtracting 4 pi r squared rho of r, and another function won't be subtracting that, and so on and so on. And there's like 10 different functions. Yeah, there's 10 different functions, but they're all related by different analytic expressions, so you can transform between them.
Here, whatever G of R, that is exactly.
So are there any more questions? Not till you get to hands-on time. Then there's the next question. Okay.
D of R. That is exactly capital G of R.
So we have a tea break, and maybe during the tea break we can have a photograph.
Yeah.
Now is a good time. We will assemble outside and take a picture.
Was to do hands-on activity for data reduction using PDF GetX3. But unfortunately, we haven't been able to get you the software and the files that you need. So this afternoon, when she has access to the internet, Nupur will upload some software and upload some files, and that will be what we'll use for the hands-on data reduction. So PDF GUI, that's for modeling. So that assumes that you've got a PDF, you've got a GVAR file, and you're fitting a model to it. But the question we've been dealing with today is not how to model the PDF, but how to get the PDF from raw data. So if you've done an experiment on your X-ray machine, and you have some raw data from the X-ray machine, and you want to get a PDF. So the software that we use, and the one I just described, is PDF GetX3. And what I've done is I've sent to Nupur copies of the software, which is for a 64-bit Windows machines. I think most of you have that. So if you have 64-bit Windows, you'll be able to download these files, and they're in the form of they're called somefile.egg. So this is an example, but the one that you'll see will not be exactly that. And you need to have Python installed on your computer, and you need to have matplotlib and numpy, but I think that you guys mostly have that. So in order to check that, if you open up a command prompt and you type Python -- version, then that will tell you which version of Python is the default version. And then there'll be 3 different egg files. You only need one of them, but you need the one that's relevant for your version of Python. So this one is relevant for Python 2.7. There's going to be one relevant for Python 3.5 and 3.6. So you need to know which version of Python is your default version of Python. You type Python space -- version. It will tell you. And then you need to install this, and you type exactly this, easy_install, and then the file name. And there's more details at this link here. And then obviously I'll be here tomorrow to try and solve any problems, but it's actually better if you can work with each other to try and get the software installed, because it's more useful if I'm helping people to use the software than if I'm helping people to install it. So later this afternoon, you'll get an email from Nupur. It will have this information, how to get this software, and you should download the software, install the software, make sure it's working. And then tomorrow morning we'll do the hands-on session. When she sends the email, there'll be 2 zip files. They're on the Google, she'll put them on the Google Drive, I think. So one of the zip files contains the software, and the other one contains files that you're going to use to do the examples. Okay. Any questions? It's all clear? Okay, so we talked a lot about X-rays, and what I want to do now is I want to talk about neutrons. So another very useful source to use to get PDFs is actually neutrons. And actually the first PDFs were all done with neutrons. So this is a little history of the neutron. So it's actually fairly recently discovered. It was only 1932 when the neutron was discovered. So at that time, the model that people had of the atom was that it had a dense core, and then it had electrons moving around the core in some kind of orbitals. And what the scientists discovered at that time was actually that they knew about protons, and that there was actually protons in the nucleus, and these contained a charge. And they knew about atomic number from the periodic table,
But what they noticed was that the mass of the atom didn't scale with the atomic number. So what that meant was that they used kind of forensics. They just did thought experiments. They said, well, if the mass doesn't, if the nucleus is made of protons, and we know the mass of the protons, and each proton has a charge, and we know the charge, we know how many protons are in the nucleus, and then we know the mass of the atom, but that doesn't agree with the measured mass. So actually they inferred that actually there must be the existence of some other particles which don't carry charge. So these are neutrons, and actually Rutherford thought they were nuclear electrons. So he actually thought that there were additional protons present in the nucleus, but there was also additional electrons confined in the nucleus that gave charge balance. But in 1932, actually, James Chadwick discovered the neutron, and it's actually a particle in its own right. So it's a neutron particle, and actually it was discovered from beta particles, which are, of course, actually helium nuclei, which are basically containing, is it one neutron, one proton, or two neutrons? Anyway, can't remember. So yeah, so looking at radioactive decay. But 1932 is really not that long ago, and that's when neutrons were discovered. So with the advent of quantum mechanics, neutrons are particles, but actually they have a particle-wave duality. So neutrons will behave like waves even though they're particles, as will all particles. And so they have a mass. They're not massless like photons. They have no charge, and they have a spin. The wavelength of the neutron depends on its velocity through the de Broglie relation. So the h over mv is the relation to give you the wavelength of this matter wave. So that means because it's related to the speed, it's related to the kinetic energy, and that means that the kinetic energy of the neutrons, if they're thermalized, so if the neutrons are in some thermal bath, you can imagine a bath full of water, and the water is all a constant temperature. What it means is that inside the water water molecules are all moving with different velocities in different directions, but they have an average velocity, and the kinetic energy of the average kinetic energy of the water molecules is actually related to the temperature of the bath. So you heat the bath up, and you make the average velocity of the water molecules to increase, and that's when the water gets hot. But the exact same thing happens, of course, with neutrons. So what we can do is we can have neutrons in a bath, and then we can make the bath some temperature. So if we make the neutrons to have that temperature, then they'll have a particular kinetic energy, and if they have that particular kinetic energy, they'll have some particular wavelength. And it turns out that actually the kind of wavelengths we want the wavelength of the neutron to be comparable to the interatomic spacing, so that we can do diffraction. So that's just something that you need to know. And so actually the wavelengths that we typically want are something like 0.1 nanometer. And so it turns out that to get 0.1 nanometer wavelength neutrons, they need to have a temperature which is around room temperature. So we call them thermal neutrons. So if we take neutrons and we thermalize them to room temperature, then through the de Broglie relation they'll have a wavelength which is around 0.1 nanometers, which is around 1 angstrom, which is around the interatomic spacing. Now if we want to look at large-scale structures, we want even longer wavelength neutrons. And so we can actually cool down the source, so we'll make a cold source. So we make a bath of neutrons which is at a lower energy, and then we'll get these longer wavelength neutrons. And these are actually, the temperatures then are cryogenic temperatures. So this is in Kelvin, so 1 Kelvin to 100 Kelvin. And if we want shorter wavelength neutrons, we have to actually warm them up. So we thermalize the neutrons at something like 1,000 to 6,000 Kelvin. So that's called a hot source. Now, which kind of neutrons do we want for PDF? Who knows? Everyone knows, no one's saying. We want short wavelength neutrons. So we want to have neutrons that are actually a tenth of an angstrom wavelength or a hundredth of an angstrom, hundredth of a nanometer. We want neutrons that are less than 0.1. We want them down here. So we would like to get a source. We would like to get a thermal bath of neutrons, which is at 1,000 Kelvin, or preferably 2,000 Kelvin, or 3,000 Kelvin, or 6,000 Kelvin. These are extremely high temperatures. So in fact, we're able to do this. We're able to make hot baths of neutrons at these high temperatures, but technologically it's actually rather difficult, and those hot sources tend to break and not be terribly reliable. So it hasn't taken off in a very big way, but it is possible to do PDF with reactor neutrons. What's your hot source temperature, do you know?
Actually, hot source was planned, but they haven't put the hot source.
Yeah, so that...
I am looking at my beam line is looking at some theoretical source.
Yeah.
So that is basically thermal source itself.
Yeah, so you're doing the...
Not 7.8 number.
0.7.
Because I
Yeah.
can't go below that.
Yeah, so you have a thermal source, but then you're looking at the tail of the distribution. So the other thing to know is that this is the average wavelength, but there's actually a spectrum which looks like a Gaussian, and this is the wavelength of the neutrons that is at the peak of the Gaussian. But you can actually extend the wavelength range by looking at the tails of the Gaussian, either on the high side or the low side. And the price you pay is the flux, the number of neutrons goes down. So you don't like to do that. Okay, so how do you make a bath of thermal neutrons? I mean, how do you make the neutrons to be like water in a bath, all with the same temperature? So I'm going to show in a minute how we create the neutrons, but when we create them, they tend to have very high energy. So we need to cool them down. And the way that you cool them down is that you make them interact with matter. And they interact very strongly with hydrogen. So typically what we do is we put some hydrogenous material around where the neutrons come out. And the neutrons make many, many collisions with this hydrogenated material. And each time there's some inelastic collision and they lose a bit of energy until they're just making these interactions with the hydrogen atoms in there at the same temperature. So they're giving and receiving energy at the same rate. So that's how we thermalize them.
But the neutrons have average lifetime of 12 minutes. How do you deal with that?
Okay, say that again.
The average lifetime of free neutron is around 12 minutes.
Yeah.
So how do you deal with that?
So they don't stay for very long in this thing. I mean, it happens in, what's the dwell time in the moderator? I mean, it's probably less than a second. What we'll do is later we'll look at a different approach, the time of flight neutrons. Yeah, but we never get close to 12 minutes. They worry about that. There's these experiments that use very cold neutrons. And there's two things you have to worry about there. One is the neutron lifetime, because it's moving so slowly. Basically, you can walk more quickly than the neutron. So if the neutron comes out of the shutter heading down the beam pipe and you walk alongside, you'll get to the other end before the neutron does. So there's one problem is the neutron decay lifetime. It'll die before it gets there. And the other problem is gravity. It actually going so slowly that gravity acting on the neutron causes it to dip down. But for the experiments that we do, we're using much more energetic neutrons. We can neglect all these effects. So neutrons are neutral particles. They have a very small interaction with matter. So why is that? Actually, because they're not charged, they don't interact with electrons. They only interact with other nucleons. So they interact with nuclei through the weak and strong nuclear force, but basically the weak nuclear force. So the material is a solid. This could be FCC nickel or something like that. And the nuclei are so tiny in this, they're 10 to the minus 15 nanometers across. It means that actually, to a neutron, a solid material essentially looks like empty space with a few tiny, tiny dots in it. So actually, nearly all of the neutrons will fly through without, without hitting anything. But occasionally, they'll come close enough to a nucleus that they'll be able to they'll be able to interact through the nuclear forces that are very short-ranged, and that's when they scatter. So as an example, a comparison, the attenuation of low-energy or thermal neutrons by aluminum is about 1% per millimeter. So in a millimeter of material, you only lose 1% of your intensity. For X-rays, that would be 99% of the intensity would be gone. So a very nice thing about neutrons is you can make special environments like furnaces and cryostats and all kinds of fancy things like that, and the neutrons can penetrate in very easily. This is another graph that shows the same thing. I'm not sure how useful it is, but this is a log scale, and this is the electron penetration versus atomic number. This is the X-ray penetration, and then this is the neutron penetration. And one thing to notice is, apart from these like edges here, and it's for a particular wavelength of X-rays and neutrons, it basically falls down with atomic number here, but with neutrons it stays more or less constant, although there's some scatter. Just as with X-rays, the neutrons have coherent and incoherent contributions. The physics is very different. In X-rays, the incoherent scattering is mostly coming from this Compton effect. In neutrons, the incoherent scattering is coming from the fact that you have mixtures of nuclei of different isotopes. So the same element will have different isotopes, so different mass nucleus. And it turns out that the scattering cross-section for the different isotopes is very different. And if you have a solid made up of a mixture of these different isotopes, which you typically do, then you'll get this incoherent background because you won't get perfect destructive interference happening between scattering from this isotope and that isotope. And you don't have to understand it in detail, but the coherent scattering is the part we're interested in. There's also an incoherent scattering. And the rest of it is basically the same. It's the norm of the square of the amplitude gives the beam intensity. That's the same as for X-rays. Now, one slight difference is that actually this is supposed to show, this is basically a single slit experiment where you have a plane wave and then a slit and you get a spherical wave coming out. And we're going to do interference experiments between two of these. That's basically the nature of the experiment. And in the case of the neutron, because it's scattering from a nucleus which is basically like a point in space, it means that actually the form factor is uniform. And in a single slit experiment, what it means is that actually in the X-ray case, the width of the slit is fairly large. It's the size of the atom. But in the neutron case, the width of the slit is very small. It's the size of the neutron, which is like 1,000 times smaller, or 10,000 times smaller. And it has the effect that actually there's a constant form factor. So we'll come back to that a little bit. But what it means is that we instead of using the scattering power F that we use in X-rays, we use this scattering cross-section B. It's a little bit unfortunate that the neutron's diffraction was kind of developed by physicists, and they were using the language of cross-sections because that's the language that Rutherford and Chadwick and these guys were using when they were doing basic scattering experiments. But this is basically, this B squared is the scattering cross-section or the scattering power, and we can use that for X-rays or for neutrons. So the scattering length, it tells you how strongly an element scatters, and it depends on the elements and the isotopes. It depends on the energy of the it says energy independent, but it does actually depend on the energy of the neutron. And actually, we don't know how to calculate it theoretically, but we measure these cross sections. So the scattering power from X-rays looks like this f of q, and it's an integral of an exponential like this times this density, and this is the electron density of the atom. And so if you integrate just the electron density, you get this we call it the X-ray form factor here. And then the scattering amplitude from a structure, which is a set of atoms, is the form factor for the single atom times the arrangement of atoms in this exponential form. But in the case of neutrons, we don't need to do this form factor integration. We just can write it down, where this is the scattering power. So nu is the sum over all the atoms, and this is the scattering power of that atom. And then we have this exponential term. So this is the form factor. This is the Q dependence of the form factor for the X-rays. So the scattering power of the X-rays decreases with increasing Q. And that's a big problem for us when we do the X-ray experiments, because the intensity of the signal goes down in the high Q region. But for neutrons, it doesn't depend in that way. It stays constant. On the other hand, the scattering cross-section for neutrons is lower than X-rays, and the source intensity for neutrons is lower. So actually, it turns out that even with this form factor problem for X-rays, they're still very good. So the reason to use X-rays versus neutrons is not because of intensity. The intensity of the X-rays is very good. Now, if you want to find out, when you have a material and you want to do the corrections, you have to tell it what elements it's made of and what the scattering power of all of the elements is. And there's actually this very beautiful website. It's the NIST Center for Neutron Research, and it contains kind of the world standard scattering cross-sections, and it's a database of the cross-sections. And actually what it does is it takes different materials like this, and it'll give the coherent scattering cross-section, the incoherent scattering, the coherent scattering length, the incoherent scattering length, and these are the coherent, incoherent cross-sections, scattering cross-section. And this is an important one. This is the absorption cross-section. So most elements have very low absorption, and there's a few kind of nasty elements that have a very high absorption. And this is because they have actually a nuclear resonant capture. So they have a resonance for capturing thermal neutrons, and they're very highly absorbing. So this one here, for example, is helium-3. So helium-3 is not very abundant, but actually these are usual numbers. The absorption cross-section is 0.3, 0.3, 0.0005, so not hardly absorbed at all. And then helium-3 is 5,000. It's extremely unstable nucleus, and it wants to capture neutrons to make itself more stable. But if you scatter from helium, natural abundance helium, it has a very low cross-section. So how is it possible that regular helium has got a low absorption cross-section, but helium-3 has a high one? And the reason is that helium-3 is basically exceptionally rare. There's no helium-3 in natural helium, or very little. And it's because helium-3 is an unstable nucleus, like I said. That's why it likes neutrons, to make it more stable. It wants to be helium-4. And the world's supply of helium-3 has basically come from nuclear weapons programs. So there's big production of helium-3 as part of nuclear weapon generating, and there's a big problem for physicists that we were kind of taking the waste from world strife. So there's a Cold War between Russia and America, and they want to build more and more nuclear weapons, so they're making more and more fissile material, and the byproduct of what they're making is helium-3. And so they're basically throwing it away, and we're saying, don't throw it away, we need it. So they would save it and keep it, and there's a world supply of helium-3, but now there's a nuclear test ban, and there's a kind of a moratorium on making new nuclear weapons, and so the world's supply of helium-3 is gradually dwindling away, and we're desperately holding on to all of the helium-3 that we can. You also need helium-3 to make very cold temperatures in a dill fridge. So a lot of physicists, we love helium-3. And we need Armageddon and world strife in order to stay supplied with it. Hydrogen is an interesting one because the hydrogen has a negative scattering length of a moderate size, but it has an extremely large incoherent scattering length. That's why we like to use hydrogenated materials for thermalizing neutrons. So this incoherent scattering means that the neutron goes into a hydrogenated material and it's incoherently scattered all over the place. So it's like, a material looks to a hydrogenous material looks to a neutron like milk looks to you. So milk, you can't see through milk because visible light coming from the other side gets incoherently scattered all around, and so you just see that you don't see, if you shine a light at the back of milk, you don't see it on the other side. That's exactly what happens to neutrons when they go into hydrogenated material. So they hang around in there just getting scattered all over the place. So that's why we use hydrogen to thermalize them. But every single element and every single isotope has some scattering lengths, a coherent and an incoherent and an absorption cross-section, and it's all contained in this table. So for a particular wavelength of neutron, and you look across the atomic number, the coherent scattering length goes like this. And so the first thing to notice about this graph is that the scattering power for neutrons as a function of element is almost constant. So with X-rays, the scattering power goes like the number of electrons. So if the same graph for X-rays, it would be going up like this. It would be going up very steeply. But for neutrons, it stays constant. So that's a very useful thing that we make use of. And the other thing about this is that although on average it's kind of flat, you see that there's these like big oscillations up and down. So if you want to actually get some contrast between two different elements that are nearby in the periodic table, like say lanthanum and barium, if you did an X-ray experiment with lanthanum and barium, they would have almost the same scattering power. But if you do a neutron experiment, the lanthanum has much higher than the barium. So these are two reasons that we use neutrons. One reason is to see light elements when there are heavy elements in your sample, and the other is to get contrast between nearby atoms in the periodic table. This is just to say that actually nickel, when you order nickel from Alpha Isar, from the chemical company, you'll just get nickel. But the nickel you get will have some isotopic composition. This depends on things like the history of the Earth and whether the nickel came on an asteroid or when it was formed. I mean, it depends on these things, but roughly speaking, most of the nickel in the Earth's crust came to the Earth at the same time, and it's roughly the same isotopic composition. And the composition looks like this. It's actually 68% nickel 58, 26% nickel 60, and then small amounts of nickel 61, 62, and 64. And so you don't need to worry about this. What you do is you use this number up here, not these numbers down here, but it does say that if you want to actually do a special experiment where you isotopically enrich the sample, so you do chemistry and you make a sample with a single kind of nickel, then you can do that. And this is one way that you can do differential PDF measurements. So you do two measurements, you make two samples, one with nickel 58 and one with nickel 60. And they'll have different scattering lengths. The nickel 58 will have 14.4 scattering length, the nickel 60 2.8. So there's a huge amount of contrast between these two. And then that allows you to find where the nickel is in your sample if you're studying glasses, for example. And this is just the diameter here of these is telling you the scattering power. And it just shows that cobalt, nickel, and copper are next to each other in the periodic table, so they have very similar scattering lengths. and platinum is very far down the periodic table, so it has a very large scattering length. But for neutrons, actually nickel has the largest scattering length, copper and platinum are similar, and cobalt is very small. So again, by doing X-ray and neutron measurements, you can give different contrasts. So you can do an experiment where where it's predominantly nickel scattering, and when you put your sample in the neutron beam, but it's predominantly platinum scattering when you put it in the X-ray beam. I talked about that. So with neutrons, you can do single crystal diffraction, powder diffraction, you can do total scattering PDF, and you can do small angle scattering. So all of the X-ray techniques you can also do with neutrons. You have to go to a neutron source, and so these are either reactors or they're spallation sources. I'll mention that in a minute. But the data collection tends to be slow. The samples need to be large volumes, so that's a challenge for the chemists. You have to make a lot of material. And if you don't have those things satisfied, you'll get low data quality. But if you do have these satisfied, you'll get very high data quality. Neutron sources tend to have a low flux as well, so that also contributes to the slowness. So the biggest challenge is actually you typically need fairly large volumes of samples, but the latest sources like the spallation neutron source, SNS, in the US, you can actually measure small samples. Actually, they've measured some samples that are hundreds of milligrams quite successfully. All right, very quickly we're going to see how you make neutrons, so reactors and spallation sources, and then how we thermalize them. So in a reactor source, it's basically a nuclear reactor. You start with a fissile material, so it might be uranium. In order to have a very good nuclear reactor for research, for a power reactor, you want it to produce a lot of power. So you want a large core with a lot of fuel in it. But for a nuclear reactor, we want our core to be very small, but we want the flux of neutrons to be coming out of that core to be very high. So we want a very high kind of neutron density core. So the best way to do that is actually to use highly enriched uranium. So historically what happened is they would actually take weapons grade uranium, so the kind of uranium that's been enriched with uranium-235 that you could actually make a nuclear weapon out of it. And the physicists, we love that because that's actually producing very high fluxes of neutrons in a very small space. Obviously you don't want it to explode, so you make it subcritical, but your core looks like that. More recently, that's actually that's not considered to be so good because of nuclear non-proliferation considerations. We don't really want a lot of weapons grade uranium being shipped around and on lorries and trucks and trains and things like that. And when they change out the core at the nuclear facilities that still have the highly enriched uranium cores, there's basically armed guards there bringing it in, and they bring it in at night, and they don't tell anyone when it's going to arrive. It's a little tricky. But basically you have a fissile nucleus, so you have an unstable nucleus like uranium-235, and you actually send in a thermal neutron and it attaches to that nucleus, and the nucleus suddenly becomes extremely unstable, and it splits into two roughly similar sized, much smaller nuclei. And when that happens, basically a lot of energy is produced, and the energy comes out, a lot of it, in different ways, but one of the ways it comes out is highly energetic neutrons. And if we then take these neutrons here that were produced by this fission, and we thermalize them enough that they can then be captured by other uranium nuclei, then they'll also undergo fission, and we get a chain reaction. And the difference between a nuclear reactor and a nuclear weapon is that this chain reaction happens in a runaway fashion in a nuclear weapon. So the entire reaction happens in a very short period of time, and you get an explosion. But in a nuclear reactor, it happens very, very slowly. And in order to ensure that it happens slowly, you have control rods which selectively absorb the neutrons. So you control the neutron flux inside the core with these control rods, and you put the control rods in and out. And you can have a kind of a disaster like Chernobyl if for some reason the rods are pulled out and the reaction starts going too quickly and you don't put the rods back in quickly enough. So most modern reactors are fail-safe, designed to be fail-safe, but there can still be accidents. But the neutron reactors are working like this. But what you see is these guys are needed for the chain reaction. So they're a product of this fission, and then they're used again to create more fission. But here it only shows 3, so it's like 3 neutrons from this fission and then 3 new fissions. But actually, you get many more neutrons coming out, so they're not all needed for the chain reaction. So the other neutrons come out, and they're highly energetic neutrons. So what we do is we take the core here and we embed it in a big bath of D2O, which moderates it. And then outside of that we have H2O as shielding. And so this is maintained at some thermal temperature, and the neutrons are thermalized in here. And then these things here are beam tubes. So they're actually evacuated tubes made of some kind of metal that poke into this moderator, and the neutrons are like just scattering around. But if they happen to scatter in this direction, instead of being scattered again, they'll go into this tube and they'll come out of this tube. So this is, I don't know which reactor this is. I think it's maybe ILL. So this has all of these green tubes are basically thermal neutron tubes. And what they have there is they have a hot source. So buried inside here they have a graphite which is heated to, I don't know, 1,000 Kelvin or a few thousand Kelvin. And so the neutrons which make their way into that, they get thermalized at the high temperature, and then they can go out through these hot tubes. And you can also make a cold source, which is some kind of cryogenically cooled thing that's separated from the D2O. But the neutrons that make their way in there, they get thermalized at a lower temperature, and then they get taken out through these cold tubes. So this is what it looks like. A very tiny core. Like the core can be really tiny like this, surrounded by a much larger thing. And this is the kind of spectrum you get from each of these. So the thermal source is here, and this is in the wavelength kind of 1 to 10. The hot source is 0.1 to 1. The cold source is up here at even longer wavelengths. So you saw this before. There's ESRF, there's a synchrotron, there's actually the neutron source, ILL. And it's contained in a building here, and actually they maintain a negative atmospheric pressure inside that building, so you have to go through an airlock to get in there. And the reason for that is that if there's any kind of accidental release of radioactive material, it won't escape out. It will stay in the building, and then they can seal the building and decontaminate it. So you have to take care of safety. If you look down inside the reactor, I think this is also ILL, but you can see it's just basically this big tank filled with water, and it glows blue like this. This is Cherenkov scattering, which is, I don't know anything about it, but it makes the thing look very beautiful and blue. So that's how reactor sources produce their neutrons. And the source that we have here in Mumbai at the Bhabha Institute is actually a reactor source. Starting in the late 80s, they wanted to take a different, or early 80s, mid-80s, they wanted to take a different approach to producing neutrons. And what they do is they take a heavy metal target like mercury or tungsten, and you accelerate a proton to very high energy, 500 millielectron volts, and you just slam it into this nucleus. This is a stable nucleus. It's not going to undergo fission. It's not going to split apart and break. but there's a process called spallation where you're just dumping so much energy into this thing that it kind of shakes the nucleus, and the nucleus lets some particles go. So some protons come out, and some neutrons come out, and some gamma rays come out. So this process is called spallation. So you need a very high energy linear accelerator, which is accelerating protons. And this is the linear accelerator at, so this is SNS, I guess. So there's a long linear accelerator that's maybe 0.5 kilometer long or maybe longer. And then it takes the protons, they're accelerated up to high energy, and then they go around here, and then they get accumulated in this ring. This is kind of like a synchrotron, but this linear accelerator can accelerate to very high energies, but it can't tolerate very high currents. So not many protons in each acceleration, but to a high energy. So you put them into this accumulator ring, and they fly around at high energy, and you just keep adding more and more and more until you have enough to create a bunch. And then you have another kicker which pushes it out of the accumulator and sends it down here, and there's actually the mercury target sitting right there in the middle of this experiment hall. And so the pulse comes in, it hits the mercury, and you get this pulse of neutrons coming out. And then we have, surrounding that core, we have something that looks like this with all the moderators in it. And then you have the beam tubes coming out. But the spectrum that comes out is got a time structure. So it's basically a series of pulses. So the machine at SNS, it runs at 60 hertz. So 60 pulses per second come out. And for this kind of machine, you don't, it has very few neutrons per pulse, so you want to make very good use of those neutrons. And so the way you do it is you do time of flight, where instead of using the wavelength of the neutron to determine its energy, you use its velocity directly. So you know when the neutron was created. That's when the proton pulse hit the target, and you start a clock when it's created, and you let the clock run, and then the neutron comes into the moderator, then it goes down the tube, then it hits your sample, then it finally ends up in a detector, and then you stop the clock when the neutron hits the detector. And the time it took to go from the time it was created to the time it was detected, that's how long it took. And you know the distance it went because it's you know where the target is and you know where the detector is, so you know the distance, you know the time, so you can determine the velocity. If you can determine the velocity through the de Broglie relation, you can determine the wavelength. So you do time of flight experiments like that, and so you can still do all of the usual experiments like diffraction and small angle scattering, but it turns out that a key aspect of this approach from our perspective is that for this to work, you can't actually properly moderate the neutrons. So the neutrons go into a moderator, but you want them to go into the moderator and come out of the moderator as quickly as possible, because that's if you leave them in the moderator a long time to properly thermalize, you don't actually know how long they stayed in the moderator, right? And your pulse gets very broad. So basically, for this technology to work, we under-moderate the neutrons. We don't let them completely equilibrate with the moderator. So a lot of the neutrons come out looking like the thermal spectrum, but there's this long, we call it epithermal tail. There's a lot of neutrons that are a little bit too energetic. They're not thermalized. And these are the neutrons that are really, really valuable for our PDF experiments. So it turns out that actually this kind of spallation neutron source is much better for PDF experiments than a reactor in most cases. That's not to say you shouldn't use a reactor. You can do good experiments at a reactor. Here's the neutron sources around the world. I don't know why you need to rectify this, as the India is not marked. So this is I don't know, it's at neutronsources.org or something. So something went wrong. Something went wrong.
In fact, we are going to have another reactor.
You are?
On the East Coast.
I see.
at Vizag.
Okay.
That will be much far superior to the current.
Really? Yeah.
It will have slightly enriched core and other things.
Yeah. So actually, there's good options then coming. What's the time scale for that?
Time scale is maybe less than 10 years.
Yeah, so within the next 10 years, so you young people.
Design is ready already.
What's ready?
Design and everything is ready.
Yeah.
Even civil design is ready.
I see. Construction started?
At the construction and other things.
Yeah. Yeah, so it seems like for the young people, you'll be able to make use of facilities where you can do good PDF and with neutrons in India. So again, this is Kirsten's view graph, and she loves her Denmark. So this is Denmark, and this is Copenhagen, where she is right now. And this is actually Sweden. But you can cross from Denmark to Sweden by a bridge. And so this is the site of the ESS. So the big spallation neutron source in the US is SNS, spallation neutron source. But they're building a big European spallation neutron source called ESS, and it's going to be right there in Sweden. And so this is actually not, this is basically a design view. It's not the real thing. But here's the linear accelerator. There's going to be an accumulator somewhere, and I don't know where the target hall is. And this is MAX 4, which is actually the Swedish synchrotron. So again, there'll be a site here which has spallation neutrons and a synchrotron. And this is some recent webcams, so they're actually undergoing construction. And you can watch it in real time if you have enough time. It's like watching cricket. Here are the planned instruments, but I don't need to go through them. I mean, you can basically do everything. But it's going to have extremely large neutron flux. They're claiming almost comparable to a synchrotron, but I'll believe that when I see it. But that allows you to look at small samples. It allows you to do time-resolved scattering experiments. So a lot of the things that we're doing at synchrotrons, you can start doing at neutron sources. Even right now, using spallation neutron sources, we can use these advanced instruments. So this is so at spallation neutron source, we use the NOMAD instrument a lot, and we use PowGen instrument a little bit. D4 is the reactor-based instrument at ILL that we can use, and at ISIS it's GEM, Polaris, and Nimrod. So again, if you note down, this one is actually PowGen. It's not PowGen 3, but if you note down these are ones that you can use. And then what's the one at Baba? It's called HiQ. Yeah, so the one at the Baba Institute is called HiQ. And again, if you go to the website of these, you'll see an instrument scientist, and it's always okay to send an email to the instrument scientist and say, I'd like to do an experiment, can you help me prepare a good proposal? I mean, it's actually, they don't have a lot of time to really help you in that regard, so it's obviously better if you find somebody to collaborate with who's got some experience, and they can read your proposal and they can say, this part is strong, but this part is weak, change it this way, change it that way. And the other thing about having a collaborator that's got some experience is that the other thing that they care about is that the beam time is very precious, and they don't want to waste it. So they want to know that if they give you beam time, even if your scientific problem is a good scientific problem, if you're not able to analyze the data correctly, it will still be a failure, right? So again, having the collaborator who's done it before and they know that you will successfully do the analysis is very helpful. So it's actually good to find a collaborator who can help. So we can certainly help. It would be challenging if all of you email me at the same time. It would be somewhat challenging. But if there's somebody who does PDF who works with your kind of materials, that's a good person to reach out to. But otherwise, just reach out to us. I told you about the time of flight methodology, but you get you get these very funny backwards looking spectra, and then you have to like convert them to forward looking spectra, and then they look crazy like this. But then you have to do the all of the corrections. A little bit about how you collect the data. So your sample is in a container. So you put the sample plus the container. Container is often a vanadium tube. So vanadium is nice because it has a very low coherent scattering length, but a very high or relatively high incoherent one. So the scattering from vanadium has no Bragg peaks in it. It's very flat. So we like to actually load our samples in vanadium tubes, and these are actually provided by the facility. You don't have to have your own vanadium tube. So you run your main experiment, which is sample plus the container. Then you want to actually subtract the scattering from the vanadium container. So you make another experiment, which is the empty vanadium container. Now the empty container and your sample might be contained in some sample environment like a furnace or a cryostat or a high pressure cell or a magnet, something like that. So you actually want to run another experiment with the sample environment in place but no sample at all at the experimental position. Then in order to get a good normalization, so I told you it's very difficult to get a perfect normalization with X-rays. With neutrons, actually, we can get a rather good normalization because what we do is we run a vanadium rod, or a vanadium rod has very small Bragg peaks. A vanadium niobium alloy, you can make it so it has 0 Bragg peaks. And so we weigh that. We know exactly how much vanadium we have in the beam. So we can get an absolute scattering cross-section from that, and that allows us to do a perfect normalization. And for time of flight, that also gives us a spectrum shape, so it tells us the different energy neutrons scatter with different probability, and there are different numbers of them, so we get that spectral shape from that. Then we have to also do this calibration from detector position to Q, and we get, and in a similar way to the X-rays, we run a known material like nickel or silicon. We know the lattice parameter of these guys, and so that gives us these calibration values that we then reuse in these experiments. So you have to do 5 experiments to do one experiment, but you only have to do most of these things once, and then you can measure multiple samples, so it's not as bad as all that. These kind of details, you get a lot of help from the instrument scientist or from your collaborator. So we can quickly run through these things. They're very similar to the X-ray case. The time of flight to Q conversion is relating the velocity and the distance to the time, which gives you the wavelength. And so it contains parameters like the primary flight path distance, the secondary and tertiary flight path distances, and this is a formula that's used to convert it to the Q. There is a dead time correction in the neutron detectors. The neutron detectors are usually helium-3 containing tubes with a wire down the middle, so they work in a very similar way to the photon counting detectors. But what happens is that the neutron gets absorbed by the helium-3, and then it produces an ionization event, which is then detected by this high voltage wire in the middle. So it looks very like the X-ray photon counting. So in that case, you need to do this dead time correction. So neutrons have a very low absorption. That's one of their characteristics. But there is a little bit of absorption that you have to actually correct for. The PDF GEDN does these corrections. Again, multiple scattering typically is low because the neutrons don't scatter strongly. But we also tend to use very large samples because we want to get more scattering from the sample, and so we tend to actually do multiple scattering correction. We use the same kind of normalizations that were in the X-ray case. There's this funny inelasticity correction called a Platschek correction, which I don't have time to go into, but we correct for this one. And we obviously correct for the background and the parasitic scattering. I don't think I want to go through that, but coming back to this is all of the corrections are in these programs. So our program is PDF GETN, and this is for time of flight neutrons. It's a free software. Alan Soper has a similar GoodRun program, which is like GoodRun X, and we're just working on a PDF GETN3 program, which works like PDF GetX3, but for this is for constant wavelength neutrons, so reactor neutrons. And we have it actually working quite well, but it's not released yet, and there are also others. And which one of these you use will probably depend on which neutron beam line you'll be working at. Okay, so that's everything I have about neutrons, and then the last little tiny piece, which I already mentioned before in my previous talk, is if you have access to an electron microscope, you can actually do these experiments from an electron microscope. And I'm not going to go into detail in this, so you should probably contact me if you want to do it. But you have to actually use this electron microscope with a very short camera length, and that gives you the high Q. So the electrons, we typically use 200 kilovolt acceleration voltage for the electrons. That gives us a very short wavelength for the electron particles. So again, you use de Broglie relation, and you get something like 0.01 angstroms, so very short wavelength. But then we have a detector which is very small. It's a little tiny CCD detector or an image plate detector. And there are some tricks here about actually sample preparation and doing the calibrations, and I don't really want to go into too much details here, but yeah, if you have access to an electron microscope, this is a possibility for collecting data. So, what's the time?
Another 20 minutes.
Okay. Yeah. So I'm not sure if it'll even take 20 minutes, but here's some just general considerations. So I've thrown a lot at you: X-rays, neutrons, electrons. How do you know when to use one and when to use the other? So one thing is actually the most important thing between electrons and neutrons is actually this scattering length complementarity. So with X-rays, it's very, very hard to see light atoms. And the light atoms are things like carbon, oxygen, hydrogen. And these are very important atoms. If you're doing something that's organic or biological, it's basically made of carbon, nitrogen, oxygen, hydrogen. And these actually scattered very weakly by X-rays. Now don't worry, because actually when we go to a synchrotron, we have very many X-rays. So there's no problem measuring carbon, nitrogen, oxygen with an X-ray source. But the problem that you run into is when you have a material like an oxide with a heavy metal in it, like lanthanum, barium, copper oxide or something, because then you have this. You're really interested in what the oxygen is doing, because the property of the material depends on what the oxygen is doing. But the oxygen is very weakly scattering, but it's surrounded by some very heavy scattering atom like barium. And you can't just measure for a longer time to get a stronger signal on the oxygen. You can do that, but you still, your scattering pattern is dominated by this heavy scattering element. So we love to go to neutrons in that case, because actually the scattering lengths are more uniformly distributed.
This is basically information content in the pattern.
Yeah.
Depending on each element.
Yeah. And actually the best is to do both measurements, X-rays and neutrons, because they're actually, you're doing the same measurement on the same sample but using a different source. It means that you get different information from those two patterns. And different information means more information, which means that you're going to get a better structure solution. So you have a scientific question you're trying to answer, and you do one experiment, and maybe there's enough information in the data to answer your question. But sometimes there's not enough information in that data set to answer your question, then you might think about doing a complementary measurement and taking both data sets, and then maybe there's enough information like that. So this is a particular example. So these are actually Emil. I took these slides from Emil, and we do a lot of work together on these cuprates. These are high temperature superconductors, and we do a lot of work on strongly correlated electron materials. So this is kind of physics-y research. But when we do X-rays, we're always very interested in the copper-oxygen bond length. This is extremely crucial to the physics of these materials. This is the copper-oxygen bond in an X-ray measurement of this. And what you can see is, whilst we have these like beautiful sharp peaks out here, the copper to oxygen bond just looks like a background noise. It's impossible to get good information out from this little guy. And so we totally need neutrons. And it's illustrated here. So oxygen has a scattering length of 8 for X-rays, and lanthanum and barium are 56 and 57. But with neutrons, it's 6 for oxygen, and it's 5 and 8 for lanthanum and barium. So here it's almost 10 times smaller, but here it's comparable. So this is a beautiful example where neutrons can help us. In the case of cerium oxide, it wasn't so bad because we were interested in a cerium-oxygen bond, and that's actually quite strong because it involves cerium. But in this material, if we were interested in oxygen-oxygen bonds, oxygen-oxygen bonds will basically be invisible in here, because the scattering power of these things, it depends on the multiplicity, but it depends on also the product of the scattering power of the two atoms in the pair. Okay, so a pair of atoms where there's cerium on one end and cerium on the other end, the scattering power of that one is going to be 60 times 60. So it's 3,600, right? The cerium oxygen is going to be basically 60 times 8, which is whatever, but it's like 600. So 3,600 down to 600, and then oxygen is going to be 8 times 8, 64. It's like 100 times less. So the oxygen peaks are 100 times smaller than the cerium oxygen peak, which is 50 times smaller than the cerium peak. There's this other really cute thing with neutrons, that some elements have a negative scattering length. What that means is that when the scattering happens, there's a phase shift, that the outgoing neutron the phase of the outgoing neutron is flipped 180 degrees with respect to the one before. So when it goes negative, that happens. But most elements have a positive scattering length. So when you make a pair of atoms and you take the product of the pair of atoms, if one of them has a positive scattering length and the other one has a negative scattering length, you get a peak in the PDF that's negative. This never happens with X-rays. All the peaks in the X-ray case are positive. And sometimes you can make a material like this, which is some kind of mixture of different elements. This is a dielectric material that we're interested in. And basically there's a very strong titanium oxygen peak here. It contains titanium oxygen and copper oxygen. And just by chance, the composition of that peak included twice as much titanium as copper. And the titanium has a negative scattering length, which is half that of copper. And so it turns out that actually that peak, by coincidence, by chance, is actually completely absent in the neutron data, but it's nice and strong in the X-ray data. So these are things that you just have to, on the one hand, you have to try and play around with before you choose your experiment. On the other hand, you can try and use it to design a better experiment, but they're just things to think about. So I didn't have too much more. So let me just summarize. So I mean, what I tried to do this morning was tell you how we get PDF data, and then a little bit how we process it. And as I said, I was during this session going to do the hands-on session, but we'll do the hands-on session. I was going to give this lecture tomorrow, so we'll do the hands-on session tomorrow. And Nupur will send the links this afternoon. So if you can download PDF GetX3 software, download the files, and tomorrow we'll do hands-on data analysis. And if you have your own data, then you should be able to try and do this analysis on your own data. While I'm still here, I can help you.
So, any question or please?
Yeah.
Negative peak in case of X-ray present anywhere. I didn't tell you, sir. In case of X-ray scattering, does negative peak in the PDF represent any pair?
To peak in the PDF.
In case of X-ray scattering, negative peaks in PDF represent any pair?
I'm still not getting it in the pair. Yeah.
Sir, for the PDF from X-ray data, does the negative peak?
Oh, negative peak. Oh, I see what you're saying. Yeah. So you're saying that you can see negative peaks, but I'm saying that there's no negative peaks.
X-ray not possible.
Okay, so no, but it's an interesting question. Like this is 0, right? This is 0, and so this looks like a negative peak, right? So that's a very good question. Yeah. So it actually turns out that we have different definitions for these correlation functions. So this is G of R, and G of R is basically what we do is it's a correlation function. So a correlation function tells you the deviation from some average, right? So you have some average behavior, and then you have some deviations from the average. And with this particular definition for this function, what we do is we set the average to be 0. And so the deviations,
they always oscillate above and below 0. But when I say that there are no positive peaks in the X-ray, what I mean is that actually there's this baseline down here which goes like minus 4 pi r rho 0, and the peaks are always positive with respect to that baseline. So there's a baseline that goes down negatively like this, and all of the peaks are sitting up above that. And with the neutron case, this minus 4 pi r rho 0 goes down like this. So there actually are some negative peaks. But it's a very good, it's a subtle point, it's a good question.
What does negative coherent length signify?
Yeah. So I mean, with all scattering events, you have a wave that comes in, and then it excites something, which emits another wave that comes out. So for X-rays, a plane wave comes in, electron starts oscillating, it emits a spherical wave that comes out. Now, the incoming wave has a phase, so it has a high peak and a low peak and a high peak and a low peak. And the wave that's going out, it also has a phase. It has a high peak and a low peak and a high peak and a low peak. And what can happen is that this scattering process can change the phase of the peak so that it can shift the phase. So X-ray scattering, for example, it shifts it exactly 180 degrees. So when the incoming wave has a high peak, the outgoing wave has a low peak, and vice versa. So all X-ray scattering has basically this 180 degree phase shift, and because it's always the same, we basically ignore it. We don't put a negative in front of every number. But in the neutron case, it really just depends on the particular interaction of the neutron with the nucleus. And in most cases, you don't have that phase shift. And in some cases, you have that phase shift, and it's kind of inverted.
It's still coherent.
It's still coherent, yeah. So does anyone have questions about how they can get access to facilities?
That's why we use a Fourier inverse case in case of Newton with Fourier inverse?
Yeah, well, we use Fourier inverse space for both. That's not a neutron. That's not an X-ray versus neutron situation. So, in a later lecture, I'll go into how the scattering happens. I haven't. So I did things a little bit in the wrong order in some sense because I haven't talked about the scattering and these scattering equations and why they look like exponentials. But I'll go through that, and that will show you where the Fourier relationship comes from. But that's not an X-ray versus neutron situation.
The copper oxide bond length in this compound, calcium, cupric, titanium,
yeah,
is it same as in cupric oxide? If you have pure copper
yeah.
oxide?
Yeah, it's very similar, right? This is two angstroms right there, so it's like 1.95 or something, so it's very, very close.
We also measured some copper tellurite glasses.
Oh, you did?
And
Yeah.
we found bond lengths.
Yeah.
Amandeep, you measured copper tellurite glasses. So what was the copper oxygen bond length?
So 1.98.
1.9?
1.95, yeah, so that's right there. Yeah.
From RMC we got it.
Yeah.
So let us thank Professor Brinji for excellent lectures. So tomorrow again we meet at 9:15, and kindly bring your assignments. So I will collect it. Tomorrow is sufficient or you want more time? So tomorrow you bring the assignments, the answers.
Okay, so there was assignment 1 you were handed, there was assignment 2, but you can't do assignment 2 yet, so don't worry about assignment 2.
Well, there is a worksheet on scattering principles.
Yeah, so the worksheet, I think if you can complete assignment 1 and the worksheet, and then tomorrow if you can bring your computer, if you can download the software, everything, the PDF GetX3 software and the files, and make sure it's working, and then bring your computer tomorrow, then that's good. So the only thing you have to hand in is the worksheet, and yeah, you have to read those first 2 chapters.
So tomorrow I collect that worksheet.